Imagine staring up at the night sky on a clear, quiet evening, tracing the familiar constellations and feeling that profound connection to the cosmos that has captivated humanity for millennia. You spot what appears to be a distant star, steadfast and luminous, and in that moment, you believe you're witnessing a genuine celestial body millions of light years away. But what if I told you that star might not be a star at all? It could be a cosmic illusion, a trick of light, gravity, or space-time so convincing that it has fooled even the most brilliant scientists and advanced telescopes. These are not simple errors or misunderstandings. They are sophisticated deceptions woven into the very fabric of the universe, challenging everything we think we know about reality. From gravitational mirages that bend starlight into phantom images to mysterious signals from deep space that mimic artificial messages, the cosmos is a master illusionist, and we are its captivated audience. These cosmic illusions do more than just surprise us. They reveal the limits of human perception and the humbling truth that our understanding of the universe is still in its infancy. For every breakthrough in astronomy, there is a corresponding mystery that reminds us how much remains unknown. These deceptions have led researchers down false paths, sparked heated debates, and occasionally reshaped entire scientific theories. They force us to question not only what we see but how we see it, pushing the boundaries of technology and imagination. In a way, these illusions are the universe's way of keeping secrets, inviting us to look closer, think deeper, and stay curious. They teach us that the cosmos is far stranger and more wonderful than we could ever imagine, filled with phenomena that defy easy explanation and invite endless wonder. In this video, we will journey through 40 of the most mind-bending cosmic illusions that have tricked experts and captivated the world. We will explore gravitational lensing that creates ghostly multiple images of distant galaxies, phantom radio signals that mimic alien communication, and vanishing stars that challenge our models of stellar evolution. Each illusion tells a story, a puzzle that required ingenuity, collaboration, and sometimes a healthy dose of skepticism to solve. This is not just a list of curiosities. It is an invitation to see the universe through new eyes, to embrace the mystery and majesty of space, and to appreciate the relentless human drive to uncover truth. So settle in, open your mind, and prepare to question everything you thought you knew about the cosmos. The journey begins now. Think of cosmic illusions not as simple mistakes or errors in judgment, but as the universe's own magic tricks, performed on a scale so vast they can confound even our most advanced technology. These phenomena occur when the normal rules of perception break down, often because we are trying to observe something incredibly distant or governed by physics that challenges our everyday intuition. The primary culprits behind these grand deceptions are the fundamental forces and properties of the cosmos itself, the bending of light by gravity, the distortion of space-time around massive objects, and the sheer vastness of cosmic distances that can turn a single point of light into a profound mystery. Even the instruments we build to extend our vision have their own limitations, sometimes introducing artifacts or noise that masquerade as genuine celestial signals. This means an astronomer studying a distant galaxy might see a double image where only one exists, or a signal that appears artificial could simply be a natural pulsar repeating with clockwork precision. These illusions are not failures of science. They are an inevitable part of exploring the unknown, serving as both a humbling reminder of our limitations and a powerful catalyst for discovery. Each time we unravel one, we are forced to improve our telescopes, refine our models, and sometimes even rewrite the textbooks, ultimately leading to a richer and more accurate picture of the universe we call home. Now, let's turn our attention to the very first illusion on our list, one that fundamentally altered our understanding of the cosmos and showcases the universe's talent for grand-scale deception: the gravitational mirage. This phenomenon is a direct consequence of Einstein's theory of general relativity, which revealed that gravity is not just a force but a warping of the very fabric of spacetime itself. Imagine spacetime as a vast, taut rubber sheet. When you place a heavy object on it, like a bowling ball, it creates a deep dimple. Now, roll a tiny marble past this bowling ball. Its path will curve around the dent, not because of a direct pull, but because it's following the curved surface. In the cosmic arena, that bowling ball is an immensely massive object, a galaxy or even an entire cluster of galaxies, and the marble is a particle of light, a photon, traveling from a distant star or quasar billions of light years behind it. The gravity of this foreground mass bends the space around it, and as light from the background object travels through this warped region, its path is curved, acting like a colossal lens. We call this breathtaking effect gravitational lensing. This cosmic lens doesn't just slightly distort the light, it can create spectacular and bewildering illusions. Instead of seeing a single, faint smudge of a faraway galaxy, astronomers might observe multiple, brighter, and sharply defined images of it arranged in a perfect circle, known as an Einstein ring, or as symmetrical arcs sweeping across the sky. In one of the most famous and beautiful examples, a quasar known as Q2237+303 appears to us not as one object, but as four distinct images forming a cross-like pattern around a closer galaxy. This configuration is poetically named the Einstein cross. When it was first observed, it presented a genuine puzzle. Researchers had to ask themselves, were they looking at four separate but identical quasars miraculously aligned? Or was it one single object, its light expertly manipulated and multiplied by the gravitational field of the intervening galaxy? It was, of course, the latter, a brilliant illusion that confirmed a profound prediction of relativity. But the story of gravitational mirages goes beyond just creating pretty pictures. They have been instrumental in uncovering one of the greatest mysteries in modern physics: dark matter. Astronomers studying the immense clusters of galaxies that act as these natural lenses noticed something peculiar. The amount of distortion they observed, the way the background galaxies were stretched and twisted, was far more extreme than could be explained by the gravity of the visible matter alone. The stars and hot gas we can see simply didn't account for the sheer depth of the gravitational well required to bend light so dramatically. This could only mean one thing: there had to be a huge amount of invisible mass, a substance that neither emits nor reflects light, enveloping these clusters and providing the extra gravitational muscle. This was some of the most compelling early evidence for the existence of dark matter, a shadowy component that makes up about 85% of all matter in the universe, forever hidden from our telescopes except for its gravitational influence. These mirages continue to challenge and aid astronomers in equal measure. They complicate the seemingly straightforward task of measuring cosmic distances, as a lensed object can appear brighter and closer than it truly is. Yet, they also provide a powerful tool for weighing the most massive structures in the universe and for peering further back in time than would otherwise be possible, acting as a natural telescope that magnifies the faint glow of the infant cosmos. The gravitational mirage is a perfect example of a cosmic illusion that initially tricks us, only to ultimately reveal a deeper, more astonishing truth about the fundamental architecture of reality. Just as gravity can bend light into deceptive shapes, the universe has another trick up its sleeve, one that plays not on our eyes but on our ears, or more accurately, on our radio telescopes. This brings us to our second great cosmic illusion, the phantom signal. In the silent, vast expanse of space, a perfectly regular, repeating pulse is one of the most exciting things an astronomer can discover. Its artificial-seeming rhythm is a potential calling card, a beacon that screams technology, and therefore intelligence. This is precisely why, in 1967, a young doctoral student named Jocelyn Bell Burnell found her heart racing. She was reviewing data from a radio telescope she had helped build when she noticed it, a series of sharp, precise pulses arriving every 1.337 seconds with a regularity more perfect than any natural celestial clock she had ever encountered. The signal was so unnervingly steady that she and her supervisor, Anthony Hewish, half-jokingly labeled it LGM-1, short for Little Green Men. The tantalizing, almost terrifying possibility hung in the air had they just made first contact. The truth, while perhaps less sensational, was no less revolutionary. They had not found aliens, but they had discovered the first of a new class of stellar object, a pulsar. A pulsar is the incredibly dense, rapidly spinning corpse of a massive star that went supernova. What remains is a neutron star, a ball of matter so compact that a single sugar cube-sized piece of it would weigh as much as a mountain. As this neutron star spins, it acts like a cosmic lighthouse. Beams of intense radiation shoot out from its magnetic poles, and if one of those beams happens to sweep across Earth during its rotation, our telescopes register it as a blink, a pulse. From our distant vantage point, we see this as a remarkably steady, rhythmic ticking. The illusion of an artificial signal is born from its very perfection. Nature, in this extreme state, can produce a rhythm more reliable than the most precise atomic clock built by human hands. The story of LGM-1 is not a historical footnote but a recurring theme in modern astronomy. Even with our advanced knowledge, new pulsars are discovered regularly, and their signals can still cause a momentary stir. Modern search for extraterrestrial intelligence, or SETI, programs use sophisticated algorithms to sift through immense volumes of data, looking for that telltale sign of an engineered signal, something narrow in frequency, drifting in a way consistent with a planet in motion, and crucially, persistent and non-natural in its pattern. A newly found pulsar can tick every single one of those boxes before it is officially identified. This means that even today, a blip on the radar from a distant, unknown pulsar can send a ripple of excitement through the scientific community before it is cross-referenced with catalogs of known objects and revealed to be just another fascinating but natural cosmic phenomenon. This particular illusion teaches us a profound lesson about our place in the universe and the nature of discovery. It underscores a fundamental challenge in the search for other intelligent life. The cosmos is already filled with naturally occurring wonders that are strange beyond our imagination. The universe doesn't need little green men to be fascinating. It can create spinning stellar zombies that broadcast with unimaginable power and precision. The phantom signals from pulsars keep scientists honest, forcing a rigorous process of verification and reminding us that the most thrilling discovery is not always the one we hope for, but the one that fundamentally changes our understanding of physics. It is a humbling and exhilarating reminder that nature itself is the greatest illusionist, capable of crafting signals so perfect they mimic the very essence of intelligence. While the universe can craft illusions of phantom signals, it also holds stars that perform the ultimate magic trick, a stunning and complete disappearance from the sky. This brings us to our next cosmic deception, the enigmatic behavior of variable stars that don't just flicker but seem to vanish into thin air. Most variable stars follow predictable rhythms, pulsing with the steady regularity of a heartbeat as they expand and contract over days or years. They are the metronomes of the cosmos, their predictable brightness changes allowing astronomers to measure vast intergalactic distances. But then there are the rebels, the stellar outliers whose behavior is anything but predictable. These stars can plunge into periods of profound dimming, fading from view so dramatically and for so long that they appear to have been snuffed out entirely, only to mysteriously return to their former glory months or even years later, as if nothing ever happened. The master of this particular vanishing act is a rare class of star known as our Coronae Borealis variables. Imagine a star that is tremendously hot, luminous, and wealthy beyond belief, not in gold but in carbon. Deep within its furnace-like interior, nuclear fusion creates a surplus of this element. Occasionally, this carbon is dredged up to the star's surface, where the intense heat can suddenly, and without warning, cause it to condense into clouds of sooty dust, much like smoke billowing from a candle flame. In a breathtakingly short time, this cloud of carbon dust expands around the star, forming a shroud so thick and opaque that it completely blocks the star's light from our view. To an astronomer watching from Earth, it's as if a celestial light switch has been flipped off. The star, once a clear point of light in a familiar constellation, is simply gone. For early observers armed with nothing more than telescopes and notebooks, these events were utterly bewildering. Without an understanding of these internal stellar processes, the sudden disappearance of a star was often interpreted as a catastrophic final event. A star that vanished was assumed to be a star that had died, perhaps in a titanic supernova explosion that had somehow been missed. In other cases, the star's dramatic return to brightness after a long absence was mistaken for a nova, a completely new star appearing where none had been before. These misclassifications were more than just simple errors. They represented significant missed opportunities. Every time a new star was catalogued where an old one had simply dimmed, it muddled the true rate of stellar explosions and distorted our early maps of stellar life cycles. It created an illusion of a far more violent and unpredictable cosmos than actually exists. Unraveling this mystery required a shift in perspective and, most importantly, the virtue of patience. It was only through dedicated, long-term monitoring of the night sky that astronomers began to notice a pattern. The same stars that disappeared would, time and again, slowly re-emerge from their self-imposed exile. This revealed that they weren't dying at all. They were merely undergoing a temporary and spectacular phase of their evolution. The illusion of their death taught us a crucial lesson about the dynamic and often messy processes that occur within stars. It underscored the absolute necessity of persistent observation, proving that to understand the true nature of the cosmos, we must watch it not just for nights or years, but for decades and even centuries. The story of the vanishing star is a powerful testament to the fact that in astronomy, sometimes the most profound truth is revealed not in a single, brilliant flash, but in the patient recording of a slow and gradual return. Moving from stars that vanish to signals that deceive, we encounter one of the most active and thrilling frontiers in modern astronomy, the hunt for planets orbiting distant suns. The primary tool in this search is a technique as elegant as it is simple, known as the transit method. Imagine an alien civilization far away, its telescope pointed at our solar system. As our planet Earth passes directly between its star, our sun, and that distant observer, our world blocks a tiny, almost imperceptible fraction of the sunlight. From that far-off vantage point, the sun would appear to very slightly dim, just for a few hours before returning to its normal brightness. We use this exact same principle to find exoplanets. Our telescopes stare unblinkingly at thousands of stars, meticulously measuring their brightness and waiting for that telltale, periodic dip that suggests an orbiting world is crossing our line of sight. It's a powerful method that has allowed us to discover thousands of planets, but it is also a method riddled with cosmic traps and false leads, where the universe loves to present convincing illusions. The problem is that a dip in a star's light is just a dip. It doesn't come with a label explaining its cause. While a planet is one perfectly valid reason, it is far from the only one. One of the most common culprits is a binary star system. If the star you're monitoring has a faint, unseen stellar companion, a smaller, dimmer star like a red dwarf, and that companion star itself has a planet, the transit of that planet can cause a dip. But so can an eclipse within the binary system itself. If the two stars orbit each other and one passes in front of the other from our perspective, the resulting dip in light can be shallow enough to perfectly mimic the signal of a giant planet, leading astronomers to announce a new world that is, in reality, just a hidden star. Then there are the tantrums of the stars themselves. Our sun is not a perfectly smooth, featureless ball of light. It is covered in dynamic, magnetic blemishes called sunspots. These are cooler, darker regions that rotate in and out of view. A large, persistent star spot rotating across the face of a distant star can cause a dip in brightness that looks almost identical to a planetary transit. The deception becomes even more convincing when that star spot is stable and rotates into view on a regular schedule, mimicking the precise orbital period of a hypothetical planet. Instrumental noise adds another layer of complexity. The sensitive electronics in a space telescope like Kepler or TESS are operating at the very edge of their capability, measuring changes in brightness of less than 1%. A random glitch, a cosmic ray striking the detector, or even subtle temperature changes within the telescope can create a tiny, downward spike in the data that, to an automated algorithm desperate to find patterns, can look tantalizingly like a planet. Perhaps no case illustrates the sting of this cosmic deception better than the story of Alpha Centauri b. In 2012, the astronomical world was electrified by the announcement of a planet orbiting one of our very closest stellar neighbors, a sun-like star just over 4 light-years away. The data suggested a rocky world, even larger than Earth, orbiting its star in a scorchingly fast 3.2 days. The discovery was hailed as a monumental breakthrough, a next-door neighbor in the galactic sense. But the triumph was short-lived. Other teams of researchers scrambled to confirm the find using different methods, and the signal began to crumble under closer scrutiny. The subtle, rhythmic dimming attributed to a planet was eventually shown to be far more likely caused by the chaotic, bubbling activity on the surface of Alpha Centauri b itself, a symphony of stellar flares and shifting star spots that had conspired to create a phantom rhythm, a ghost in the data masquerading as a new world. The planet was retracted, a sobering reminder of how easily hope and data can become entangled. These red herrings are not failures, they are an essential part of the scientific process, forcing a higher standard of proof and driving innovation. They have led to the development of a multi-step verification protocol that is now standard practice. A dip in light is no longer enough. Astronomers must now seek confirmation using other techniques, such as the radial velocity method, which looks for the telltale wobble a planet's gravity induces in its host star. They run complex statistical models to determine the likelihood of the signal being a false positive. They may even use multiple telescopes to observe the same star, ensuring the signal isn't an artifact of a single instrument. This rigorous detective work transforms the search for exoplanets from a simple game of pattern recognition into a sophisticated forensic investigation of starlight. Every cosmic red herring that is caught and identified makes our methods sharper, our instruments better, and our eventual discoveries of truly Earth-like worlds far more certain and profound. Yet, even as we refine our methods for finding new worlds, we must also confront a far grander and more fundamental cosmic measurement, one that seeks to describe the very evolution of the entire universe. This brings us to our fifth great illusion, a deception not of a single star or signal, but of the cosmos's most basic behavior, its expansion. The story begins with Edwin Hubble's groundbreaking discovery in the 1920s. By observing that light from distant galaxies was stretched or redshifted, he realized they were all rushing away from us. The farther away a galaxy was, the faster it appeared to be receding. This led to the formulation of the Hubble constant, a single number that represents the rate of this expansion and, by extension, allows us to calculate the age of the universe itself. It seems like it should be a straightforward measurement, a fundamental pillar of cosmology. But in reality, pinning down this number has become one of the most stubborn and contentious puzzles in modern science, a classic case of the universe presenting us with conflicting, illusory data. The primary tool for measuring this expansion is redshift. As the universe stretches, the wavelength of light traveling through it gets stretched too, shifting it toward the red end of the spectrum. A greater redshift means the galaxy is moving away faster, indicating it is farther away and that more space has expanded between us. The illusion arises because this clean, smooth picture of an evenly expanding cosmos is often muddied by local reality. Galaxies are not simply passive dots on an expanding grid. They have their own individual motions known as peculiar velocities. They are tugged and pulled by the gravitational influence of their neighbors, massive galaxy clusters, and vast cosmic voids. Our own Milky Way, for instance, is being pulled toward the immense gravitational attractor known as the Great Attractor. This means a galaxy's observed redshift is a combination of the cosmological redshift from the universe's expansion and the Doppler shift from its own peculiar motion. If we mistake a galaxy's peculiar velocity for pure cosmic expansion, we can severely misjudge its distance and, consequently, miscalculate the expansion rate. It's like trying to measure the steady current of a wide river while ignoring the powerful, swirling eddies and local whirlpools that affect any single leaf floating on its surface. This local chaos has fueled a major crisis in cosmology known as the Hubble tension. For years, scientists have used two primary methods to measure the Hubble constant, expecting them to converge on the same answer. The first method looks into the ancient universe using the detailed snapshot of the cosmic microwave background, the afterglow of the Big Bang, as a starting point. By plugging this data into our standard model of cosmology, we can predict how fast the universe should be expanding today. The second method looks at the modern universe using what are called standard candles, objects like type Ia Supernova or certain variable stars whose intrinsic brightness we know. By measuring how bright they appear from Earth, we can calculate their distance accurately, and by comparing that to their redshift, we can measure the expansion rate directly. The problem: these two methods give stubbornly different answers. The local measurements suggest a faster expansion rate, while the early universe measurements suggest a slower one. The discrepancy is beyond any reasonable margin of error, implying that one or both methods are being tricked by an illusion we don't yet understand. This isn't just an academic debate over decimal points. It strikes at the heart of our understanding of cosmic history. If the local measurements are correct, it could mean our standard cosmological model is incomplete. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant but has evolved over time. maybe there is a new type of neutrino or another exotic particle influencing the expansion history. On the other hand, if the early universe measurements are being deceived, it could mean our understanding of the standard candles is flawed. Perhaps type Ia supernova are not as standard as we thought, or maybe there is unseen dust dimming their light and skewing the distance calculations. The illusion of a varying expansion rate forces cosmologists to question their most basic assumptions. It reveals that even our most fundamental cosmic yardsticks can be warped by effects we haven't fully accounted for, turning a simple number into a profound mystery that may ultimately require new physics to resolve. Now, let's journey from the grand scale of the expanding universe down into the heart of a single galaxy, where another profound cosmic illusion awaits us, one that has fundamentally reshaped our understanding of the very nature of matter. This is the story of the ghostly galactic rotation curve, a puzzle so baffling that it forced astronomers to invent an entirely new form of physics to explain it. The principle at play seems beautifully simple, grounded in the same orbital mechanics that govern our solar system. Think of Mercury, the innermost planet, whipping around the Sun at a blistering 47 kilometers per second. Now contrast that with Neptune, the outermost planet, plodding along at a leisurely 5.4 kilometers per second. This difference makes perfect sense. The Sun's gravitational grip weakens with distance, so objects farther out feel a weaker pull, and to avoid flying off into space must move more slowly. For over a century, astronomers assumed this same rule would apply to galaxies. The stars orbiting a galactic center, they reasoned, should behave just like planets around a star. The stars closer to the bright, dense core should be zipping along quickly, while those in the sparse, dark outer reaches should be crawling. When technology finally advanced enough to test this hypothesis in the 1970s, the results were not just surprising, they were universe-altering. Astronomers like Vera Rubin began meticulously measuring the velocities of stars and clouds of hydrogen, gas at different distances from the centers of spiral galaxies. They plotted these speeds against their distance, creating what is known as a rotation curve. According to Newtonian gravity and Kepler's laws, this curve should have been a clean, downhill slope. But the data revealed something astonishingly different. Instead of dropping off, the rotation curves were flat. Stars and gas clouds on the very outskirts of a galaxy, far beyond the visible disk of stars, were moving just as fast as those near the center. It was as if Neptune were hurtling around the Sun at the same speed as Mercury, defying all logic and physics as we knew it. The only possible explanation was that there had to be far more gravity out there than could be accounted for by the glowing stars and gas we could see. This invisible source of gravity, this ghostly mass, was given a name: dark matter. This discovery is one of the cornerstones of modern cosmology, but the path to accepting it was not straightforward and is filled with its own subtle deceptions. The illusion here is not the flat rotation curve itself. That observation is rock solid. The illusion arises from our powerful desire for a simpler, more elegant explanation. The idea that 85% of the matter in the universe is made of some unknown, invisible particle that doesn't interact with light is, frankly, a fantastical and unsettling proposition. This has led some brilliant physicists to propose an alternative, that we don't need dark matter at all. Perhaps, they argue, our understanding of gravity itself is incomplete on the vast scales of galaxies. Theories like modified Newtonian dynamics, or MUND, suggest that gravity behaves differently when it becomes incredibly weak, as it is in the outer reaches of a galaxy. This modified law of gravity can be tweaked to produce a flat rotation curve without requiring any extra invisible mass. For a time, MUND created a compelling illusion of its own. It seemed to offer a simpler, more parsimonious solution. By adjusting the equations of gravity, proponents could make the rotation curves of many galaxies fit their model beautifully, tricking some scientists into believing they had found a way to avoid the need for exotic dark matter. It was a seductive idea, a single tweak to a fundamental law versus the invention of a whole new, undetectable universe of particles. However, as our observations have grown more sophisticated, the cracks in this alternative have begun to show. Weilmann can explain the rotation of many individual galaxies quite well. It struggles mightily to account for other, even more powerful lines of evidence for dark matter. For instance, when we observe massive galaxy clusters colliding, the gravitational lensing effect shows us clearly that the vast majority of the mass, the stuff that bends the light, is completely separate from the visible matter. The hot gas from the collision slows down, but the gravity, dictated by the dark matter, just keeps going. Weilmann has a very difficult time explaining this and other large-scale phenomena, like the precise patterns seen in the cosmic microwave background. The ghostly rotation curve, therefore, presents a double illusion. First, it revealed the illusion that galaxies are made only of what we can see. Then, it spawned the secondary illusion that a simple modification of gravity could make the problem disappear. This ongoing tension between dark matter and modified gravity is not a weakness of science, but its greatest strength. It represents a rigorous, decades-long process of testing and verification. The initial illusion of a simpler answer forced dark matter proponents to sharpen their theories, to predict exactly what dark matter should and shouldn't do, and to go out and find corroborating evidence across multiple cosmic arenas. This back and forth has ultimately made the case for dark matter stronger, even as the particle itself remains elusive. The galactic rotation curve stands as a permanent monument to a universe that is far weirder than we ever imagined, reminding us that the most fundamental rules of reality are still being written, and that sometimes the most elegant solution is not the simplest one, but the one that accounts for all the ghosts in the machine. Now let's venture into the realm of the truly theoretical, where the fabric of reality itself might contain flaws left over from the universe's fiery birth. This brings us to our seventh cosmic illusion, one that involves not just misread signals but the very structure of spacetime. Picture the early universe not as a smooth, expanding fireball, but as a seething, chaotic froth of energy undergoing a series of rapid phase transitions. Much like water freezing into ice, these shifts in the state of the cosmos could have created cracks or defects in the very fabric of spacetime. Theorists have given these hypothetical one-dimensional flaws a captivating name: cosmic strings. These wouldn't be strings in any ordinary sense. Imagine them as unimaginably thin, incredibly dense filaments of pure energy, thinner than a proton but with the mass of a mountain range packed into every mile. They would be under immense tension, and their gravitational influence would be so profound that they could warp the space around them, creating unique and detectable signatures across the cosmos. For decades, the hunt for these cosmic strings has been a thrilling, albeit elusive, pursuit. The primary way to find them would be through their gravitational effects. A cosmic string drifting between us and a distant galaxy would act like a peculiar gravitational lens. Instead of creating the arcs and multiple images associated with a massive object like a galaxy cluster, a string's unique geometry would theoretically produce a very specific kind of double image, a perfectly identical twin of a background galaxy or quasar, split right along the string's edge. On another front, scientists scouring the cosmic microwave background, the oldest light in the universe, looked for telltale linear patterns or sharp step-like discontinuities in its temperature. Finding such a signal would be like discovering a fossilized crack in the infant universe, a direct window into physics at energies far beyond anything we can recreate in a particle accelerator. The potential discovery was so monumental that it drove a significant part of cosmological research for years. The history of this search, however, is littered with tantalizing false positives mirages that sparked waves of excitement before dissolving under closer scrutiny. There have been several instances where teams analyzing data from telescopes like the Hubble or Planck satellite identified a curious pair of galaxies that appeared suspiciously similar and aligned. The immediate, electrifying question was always, is this a cosmic string? In other cases, faint linear features in the microwave background maps were initially flagged as potential candidates. The desire to be the first to confirm such a profound prediction of early universe physics was a powerful motivator. Yet time and again, more detailed follow-up observations revealed a more mundane truth. Those twin galaxies were just a chance alignment of two unrelated objects. The linear feature in the background radiation was an artifact of the telescope's instrumentation, or the complex process of subtracting foreground dust from our own galaxy. What seemed like a crack in space-time was in reality a crack in the data processing pipeline. These episodes serve as a powerful case study in the psychology of scientific discovery. They highlight the delicate and often treacherous balance between prediction and perception. When a scientist has spent years developing a beautiful, elegant theory like cosmic strings, there is an inherent and very human desire to find evidence for it. This desire can sometimes create a kind of perceptual bias, where random noise in the data is subconsciously shaped into the expected pattern. Anomalies that would normally be dismissed are given extra weight because they fit the narrative. The cosmic string mirage teaches us that the most dangerous illusions are not always out there in the cosmos. Sometimes they are generated by our own hopes and expectations, a reminder that the rigorous, skeptical process of peer review and independent verification is our best defense against seeing what we want to see rather than what is actually there. If the idea of cosmic strings plays with the fabric of spacetime, then our next illusion takes us to the very heart of nothingness itself, to the seemingly empty void between stars and galaxies. Common sense tells us that a perfect vacuum is just that, empty, inert, and devoid of any activity or energy. But quantum physics, the rules that govern the universe on the smallest scales, paints a radically different and almost unbelievable picture. It suggests that what we perceive as true nothingness is in reality a seething, bubbling froth of temporary existence. At every single point in space, pairs of virtual particles and their anti-particle counterparts are constantly flickering into and out of existence, borrowing energy from the vacuum for an immeasurably short moment before annihilating each other and returning it. This bizarre process is known as quantum vacuum fluctuation, and it implies that empty space is not empty at all, but is instead alive with a background hum of frantic, evanescent activity. This leads to one of the most staggering and persistent problems in all of modern physics, a numerical discrepancy so vast it has been called the worst theoretical prediction in the history of science. The energy density of this quantum vacuum, often referred to as vacuum energy, can be calculated, and when theorists do the math, the value they get is mind-bogglingly enormous. It suggests that the energy contained in every cubic centimeter of so-called empty space should be enough to instantly curl the entire universe into a tightly wound ball or tear it apart at the seams. This theoretical prediction is a number followed by 120 zeros. Yet, when astronomers measure the actual energy driving the acceleration of the universe's expansion, what we call dark energy, the observed value is almost unimaginably smaller. We are talking about a difference of a factor of 10 to the power of 120. To put that in perspective, it is a discrepancy far greater than the difference in size between a single proton and the entire observable universe. This yawning chasm between prediction and observation is known as the cosmological constant problem, and it represents a profound failure of our two most successful theories, quantum mechanics and general relativity, to agree on the most basic property of reality, the energy of nothing. This colossal mismatch has, in turn, led to a series of more subtle experimental illusions, where the desperate search for any measurable effect of this vacuum energy has sometimes seen scientists mistake mere noise for a revolutionary discovery. Over the decades, various sophisticated lab experiments have been designed to detect the faint forces that these virtual particles should exert. One famous example involves bringing two incredibly smooth, neutral metal plates extremely close together in a vacuum. The idea, based on the Casimir effect, is that the limited space between the plates should restrict the types of virtual particles that can pop into existence, creating a slight pressure difference that pushes the plates together. While this effect has been measured and does confirm the reality of quantum fluctuations, attempts to use it to directly measure the vacuum energy's density have been fraught with difficulty. The forces involved are infinitesimally small, and what initially appear to be positive results can often be traced back to unaccounted for electrostatic forces, microscopic imperfections on the plates, or other mundane experimental artifacts. These false positives create a phantom signal, an illusion that we are on the verge of cracking the mystery, only for it to dissolve upon closer inspection, leaving the fundamental problem untouched. This ongoing challenge forces physicists to confront several deeply unsettling possibilities. The first is that our understanding of quantum field theory, while spectacularly successful in other areas, is somehow completely wrong about the vacuum. The second, more likely option is that there is a mysterious cancellation mechanism at work that we don't yet understand, a symmetry or principle that perfectly nullifies almost all of this vacuum energy, leaving behind only the tiny, residual amount we observe as dark energy. Or perhaps dark energy isn't a manifestation of vacuum energy at all, but something else entirely, like a dynamic field permeating space that theorists have named quintessence. The phantom of vacuum energy is a humbling reminder that the universe guards its deepest secrets closely, and that the void is far more complex and deceptive than it appears. It stands as a monumental puzzle that continues to fuel debates and drive innovation, proving that sometimes the greatest illusions are not what we see, but what we calculate. While we grapple with the profound mysteries of quantum nothingness, it's a startling reminder that even the most intimate and local parts of our own cosmic neighborhood are capable of grand deceptions. Far from the abstract realm of vacuum energy, a gentle, ethereal glow has been tricking sky watchers for centuries, presenting a beautiful but entirely local phenomenon as something far more majestic and distant. This is the subtle magic of the Zodiacal Light, a soft, hazy pillar of radiance often visible in the east before dawn or in the west just after sunset, stretching upward from the horizon along the path the sun and planets travel, known as the ecliptic. Unlike the sharp, defined band of the Milky Way, this glow is diffuse and pyramid-shaped, a faint and elusive luminescence that has sparked both wonder and confusion throughout human history. The source of this gentle light is surprisingly humble. It is nothing more than sunlight reflecting off countless tiny particles of dust that are perpetually falling through the inner solar system. These minuscule grains, most no larger than specks of sand, are the scattered debris left behind by comets as they streak around the sun, and by asteroids grinding against each other in the belt between Mars and Jupiter. This vast, disc-shaped cloud of interplanetary dust, concentrated along the orbital plane of the planets, acts like a colossal mirror, catching the sun's rays even when the sun itself is below our horizon. From our vantage point on Earth, we see this reflected light as a soft, otherworldly glow, a permanent but often overlooked fixture of our skies that requires exceptionally dark, clear conditions to observe. For early astronomers who lacked our modern understanding of the solar system's structure, this glow was a source of profound mystery and frequent misinterpretation. In an era before light pollution, the zodiacal light was a much more prominent feature of the night sky. Some ancient stargazers, from the Persians to the Mayans, incorporated it into their celestial mythology, perhaps seeing it as a bridge to the gods or a path for spirits. By the scientific revolution, the confusion became more technical. Renowned astronomers like Giovanni Cassini, who first described it systematically in the 17th century, initially struggled to place its origin. Some hypothesized it was a permanent atmospheric phenomenon, an ethereal vapor high in Earth's own air. Others, looking at its alignment with the planets, wondered if it was the glowing atmosphere of the Sun itself, extending far beyond the visible disk. The most fascinating misidentifications, however, ventured into the realm of pure speculation. In the 19th century, a few thinkers proposed that the zodiacal light was actually the merged glow of countless unknown stars, a ring of suns encircling our solar system. This idea, while incorrect, wasn't too far off from the true nature of distant galaxies, but it placed this cosmic structure far too close to home. Even more remarkably, in the early 20th century, as the idea of extraterrestrial life captured the public imagination, some suggested the glow could be evidence of vast alien engineering projects, a swath of constructed habitats or energy collectors orbiting our sun, catching its light. It was a classic case of the human mind leaping to the most spectacular conclusion when a simpler, dustier truth was readily available. This persistent illusion underscores a critical lesson that is as relevant today with our space telescopes as it was for those early observers with their naked eyes. Context is everything in astronomy. The zodiacal light is the ultimate foreground effect, a veil of scattered sunlight that hangs between us and the deeper universe. For modern cosmologists, it isn't just a curiosity, it's a genuine nuisance. When trying to make precise measurements of the extremely faint cosmic microwave background or map the large-scale structure of the universe, this local dust glow is a form of pollution that must be meticulously identified and subtracted from the data. If not accounted for, its subtle signal can contaminate observations, creating the illusion of large-scale anisotropies or patterns in the distant cosmos that are actually just reflections from dust motes in our own backyard. The story of the zodiacal light is a beautiful paradox. It is a breathtaking sight that connects us to the dynamic, dusty processes of our own solar system, yet its history is a catalogue of errors born from its deceptive grandeur. It teaches a humble lesson about perspective. Sometimes the most captivating glow on the horizon isn't a distant galaxy or a sign of alien intelligence, but the illuminated detritus of our own celestial neighborhood, a reminder that before we can truly see the universe, we must first learn to recognize the dust at our own feet. Human beings are hardwired to find patterns. It's a survival instinct that helped our ancestors identify predators in the tall grass or find edible plants in a dense forest. But this incredible skill, so useful on Earth, becomes a liability when we turn our gaze to the cosmos. The universe is an unimaginably vast and complex place, governed by statistics and probability on a scale that defies human intuition. This brings us to our 10th great cosmic illusion, one that preys directly on our deepest psychological tendencies, the seductive and often misleading allure of cosmic coincidence. Throughout the history of science, researchers have occasionally stumbled upon numerical relationships or strange alignments in the data so seemingly perfect, so inexplicably precise, that they appear to whisper of a deeper design, a hidden hand guiding the laws of physics. These coincidences have, at various times, tricked brilliant minds into believing they were on the verge of uncovering everything from evidence for a creator to entirely new branches of physics. One of the most famous examples of this is the series of numerical relationships known as the large number coincidences. These are ratios between fundamental constants of nature and cosmic scales that seem to line up in a way that feels far too neat to be random. For instance, the ratio of the electromagnetic force to the gravitational force between a proton and an electron is a staggeringly large number, approximately 10 to the power of 39. Astonishingly, the age of the universe expressed in fundamental time units is also a number of a similar magnitude. Another coincidence involves the number of protons in the observable universe, which is roughly 10 to the power of 80, and the square of the previous large number. To some, this felt like a cosmic signature, a hint that the universe was somehow fine-tuned, with its fundamental constants set to these specific values to allow for the eventual emergence of life. This line of thinking leads directly to the anthropic principle, the idea that the universe must be the way it is because we are here to observe it. While this is a fascinating philosophical concept, these numerical coincidences were its primary fuel. However, many physicists now see these relationships not as evidence of design, but as necessary outcomes of a universe that has evolved over billions of years. The constants are what they are, and we simply observe the consequences. The apparent coincidence is an illusion born from our desire to find meaning in immense numbers. Perhaps no modern case better illustrates the danger of overinterpreting patterns than the story of the axis of evil. This dramatic name was given to a peculiar and unsettling anomaly discovered in the most precise map of the early universe ever made, the cosmic microwave background radiation. This fossil light from the Big Bang should be almost perfectly uniform, with tiny, random fluctuations in temperature that are evenly distributed in all directions. This assumption, called the cosmological principle, is a cornerstone of modern cosmology, the idea that the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. But when scientists with the Wilkinson Microwave Anisotropy Probe and later the Planck satellite analyzed their data, they found something that sent a shiver down the spine of cosmology. The fluctuations weren't completely random. There appeared to be a curious alignment, a preferred direction in space along which these hot and cold spots seemed to correlate more strongly. It was as if the universe had a faint, ghostly axis, and this axis seemed to be aligned bizarrely with the plane of our own solar system. The implications were staggering. If true, it suggested that our place in the cosmos was not arbitrary. It hinted that either the universe had a fundamental preferred direction, breaking the cosmological principle, or worse, that there was some unaccounted for contamination from our local environment that was skewing the data. Some theorists, captivated by the strangeness of the finding, proposed radical explanations involving pre-Big Bang physics or even the influence of other universes. The scientific community was abuzz with both excitement and profound unease. However, as with so many cosmic illusions, the truth turned out to be far more mundane. As more data was collected and analyzed with even greater care, the significance of the axis of evil began to fade. The most likely explanation was a combination of two factors. First, it was almost certainly a statistical fluke. When you analyze a map with millions of pixels, some strange-looking patterns are bound to emerge purely by chance. Our pattern-finding brains latch onto them, but they carry no deeper meaning. Second, and more importantly, there were subtle systematic errors that had not been fully removed. The delicate process of subtracting the foreground glow from our own galaxy's dust is incredibly complex, and even a tiny residual signal could create the illusion of a large-scale alignment. The axis of evil stands today as a powerful cautionary tale, a reminder that the universe is under no obligation to conform to our aesthetic desire for symmetry or our deep-seated need to find a special direction that makes us feel central to the grand scheme of things. These illusions of coincidence teach us a vital lesson about the scientific method. The process of discovery isn't just about finding patterns, it's about rigorously trying to destroy them. It's about subjecting every tantalizing alignment to the most brutal statistical tests and considering the most boring explanations first. The universe is a master of deception, not because it is malicious, but because it operates on a scale where randomness can produce outcomes that look, to our limited perspective, impossibly designed. Every time we resist the urge to immediately proclaim a revolutionary discovery based on a strange alignment, and instead double down on checking our instruments and our math, we strengthen our understanding of the true underlying reality. These cosmic coincidences are the siren songs of exploration, beautiful and alluring, but they beckon us toward the rocks of error. Heeding their call without caution can lead us astray, but navigating past them with healthy skepticism is what ultimately guides us toward genuine, lasting truth. For decades, one of the most compelling scientific detective stories has been the hunt for dark matter particles. We know this mysterious substance must exist because of its overwhelming gravitational influence on galaxies, but we have never directly caught a single particle of it. This search has led to the creation of incredibly sensitive experiments, often buried deep underground in abandoned mines or beneath mountains to shield them from the constant barrage of cosmic rays and other interfering radiation. These detectors are designed to wait with almost unimaginable patience for the telltale signature of a weakly interacting massive particle, or WIMP, the leading theoretical candidate, bumping into an atomic nucleus within their core. The expected signal is incredibly faint, a mere whisper against a cacophony of background noise, and this setup is a perfect breeding ground for some of the most controversial and tantalizing cosmic illusions in modern physics. The story of the Dharma/Libra experiment is a classic case study in this elusive pursuit. Located deep under the Gran Sasso mountain in Italy, this detector has been collecting data for over 2 decades. Its claim to fame, and the source of intense ongoing debate, is its observation of a very specific signal, an annual modulation in its event rate. The number of tiny flashes of light in its sodium iodide crystals seems to rise and fall with a rhythm that peaks around June 2nd and hits a low around December 2nd. The proposed explanation is elegant and compelling. As our solar system moves through the Milky Way, it should be constantly plowing through the vast halo of dark matter that envelops our galaxy. But Earth is also orbiting the Sun at a staggering 30 kilometers per second. Around June, Earth's motion around the Sun is adding to the solar system's overall motion through the galactic halo, meaning our planet is moving headfirst into the dark matter wind. This should make the apparent flux of particles slightly higher. In December, Earth is moving in the opposite direction, with the wind at its back, so the relative speed and collision rate should be slightly lower. The Dharma team argues that their observed annual wobble in the data is the direct smoking gun signature of this exact phenomenon. For a time, this seemed like a monumental breakthrough. Here was a signal with the precise fingerprint predicted for a dark matter wind. The scientific community was electrified. However, the initial excitement soon gave way to deep skepticism and controversy. The core of the problem is that an annual modulation is a notoriously difficult signal to claim uniquely, because our planet has a very pronounced and entirely ordinary seasonal cycle. Critics pointed out that numerous subtle environmental factors also change with the seasons. The temperature and humidity in the underground lab can fluctuate minutely, potentially affecting the sensitive electronics. The concentration of radon gas, a naturally occurring radioactive element that seeps from the surrounding rock, can also vary throughout the year and create a background signal that mimics a modulation. Perhaps most crucially, dozens of other experiments around the world, using different detector technologies like xenon or germanium, have failed to see any sign of the same modulation or the specific type of signal Dama reports. They have set limits that seem to completely rule out the existence of WIMP that would interact in the way Dama data suggests. This has created a decades-long standoff, a high-stakes game of scientific chess. The Dama collaboration maintains their signal is real and robust, having now observed it for multiple full cycles, and they have painstakingly worked to rule out many potential seasonal backgrounds. Their critics argue that an unknown, overlooked systematic effect must be the culprit, an illusion created by the complex interplay of the environment and the detector itself. This ongoing debate is not a sign of failure. It is a powerful demonstration of the scientific process at work. It highlights the extraordinary challenge of searching for something that interacts so feebly with normal matter that its signal is buried in a sea of natural radioactivity and cosmic interference. Every claimed detection is met with intense scrutiny, and rightfully so. These phantom signals, these vanishing acts, are what push the entire field forward. They force scientists to build ever more sensitive detectors, to develop new methods for shielding and background rejection, and to invent creative ways to cross-check results. The hunt for dark matter has become a race not just to see the signal, but to understand the noise, to master the art of listening for a single, cosmic whisper in a hurricane of static. From the elusive whispers of dark matter, we now turn to a cosmic tool that has illuminated one of the greatest discoveries of the last century, only to occasionally reveal its own deceptive quirks. The brilliant, catastrophic explosions of dying stars known as type Ia Supernova have earned the title of standard candles for a profoundly important reason. Astronomers understand the physics behind these stellar detonations so well that they all reach nearly the same peak intrinsic brightness. This means that by simply measuring how dim a type Ia supernova appears from Earth, we can calculate its distance with remarkable accuracy. It was precisely this property that allowed two separate teams in the late 1990s to make the shocking discovery that the expansion of the universe is not slowing down, as everyone had assumed, but is actually accelerating, a finding that earned them the Nobel Prize and introduced the world to the mysterious force of dark energy. This entire method, however, relies on a critical and subtle effect predicted by Einstein's theory of relativity, time dilation. Because the universe itself is expanding, the light from a distant supernova doesn't just get dimmer on its journey to us, its very timeline gets stretched. Imagine the light curve of a supernova, the graph of its brightness over time. For a nearby explosion, this curve has a very specific shape, a sharp rise to peak brightness, followed by a characteristic gradual decline. Now, for a supernova billions of light years away, the expansion of the universe stretches the wavelength of its light, which we measure as redshift. But it also stretches the duration of the event itself. That same light curve should appear to be drawn out, slowed down, as if viewed in slow motion. A supernova that would take 20 days to fade to half its brightness in its own galaxy should appear to take 40 days to do the same if it's at a high redshift. This time dilation is a direct, observable signature of the universe's expansion, and it's a crucial correction factor that astronomers build into their distance calculations. But what happens when the universe seems to break its own rules? In recent years, as our telescopes have peered deeper and seen fainter, more distant supernovae, a handful of studies have reported puzzling anomalies. Some of these ancient explosions, lurking at the very edges of the observable universe, don't seem to be playing by the relativistic playbook. Their light curves appear to evolve a little too quickly for their redshift. The observed time dilation effect seems weaker than what the standard cosmological models predict. It's a tiny discrepancy, a faint whisper of inconsistency, but in the precise world of cosmology, even a small deviation can send ripples of anxiety through the community. The immediate, tantalizing question is whether we are seeing a flaw in Einstein's theory of relativity itself, a sign that our understanding of gravity and spacetime breaks down over the largest conceivable scales. The truth, as it often is in cosmic detective work, is likely far more mundane but no less fascinating. The illusion of inconsistent time dilation is probably not a revolution in physics, but a classic case of observational trickery. One of the primary suspects is the method used to analyze the supernova's light. Constructing a light curve from a faint, noisy signal at the limits of detectability is an art as much as a science. Astronomers use sophisticated templates and fitting techniques to match the observed data to the ideal model of a type Ia light curve. If there's any systematic error in this fitting process, perhaps because the background light from the host galaxy isn't perfectly subtracted, or because the filters used on the telescope don't perfectly match those used to define the standard template, it can subtly distort the measured width of the light curve, creating the false impression that the supernova evolved faster than it truly did. Another compelling explanation lies in the possibility that the supernova themselves are not perfectly standard. The prevailing theory is that type Ia supernova occur in binary systems where a white dwarf star steals material from a companion until it reaches a critical mass and explodes. But what if the properties of the white dwarfs or their companions were different in the early universe? Perhaps the first stars to die were slightly less massive, or made of different primordial materials, causing them to explode with a slightly faster, intrinsically narrower light curve. If astronomers mistakenly assume all supernovae are identical, and then see one from the early universe that is inherently quicker, they might misinterpret its rapid evolution as a lack of time dilation, when in fact they are just seeing a slightly different breed of stellar explosion. This cosmic illusion forces a profound and necessary humility upon us. It reminds us that the universe is a complex and evolving place, and that even our most trusted cosmic yardsticks need to be continually checked and calibrated against the deceptive shadows of the deep sky. Long before Einstein reshaped our understanding of space and time, scientists grappled with a seemingly simple question: how does light travel across the vast emptiness of space? If sound needs air or water to move through, what medium carries light from the sun to the earth? The answer, they were convinced, was a mysterious, invisible substance that permeated all of existence, the luminiferous ether. This was not a fringe idea but a central pillar of 19th century physics. Theorists imagined the ether as a static, frictionless, and perfectly transparent sea that filled the universe, an absolute frame of reference against which all motion could be measured. Light waves were thought to be vibrations in this ethereal medium, much like sound waves are vibrations in air. It was an elegant and intuitive concept, but it was also a grand illusion, one that would set the stage for one of the most famous non-discoveries in scientific history. The quest to prove the ether's existence fell to two brilliant American experimenters, Albert Michelson and Edward Morley. Their ingenious apparatus, an interferometer, was designed to detect the ether wind. The reasoning was straightforward. As Earth hurtles through space in its orbit around the Sun, it should be moving through this stationary ether sea. This motion should create a detectable ether wind, much like a runner feels wind on their face. Michelson and Morley's device split a beam of light and sent the two parts racing on perpendicular paths before recombining them. If the ether existed, the beam traveling along the direction of Earth's motion should be slowed slightly by the ether wind, arriving out of sync with its partner and creating a characteristic interference pattern. The experiment was exquisitely sensitive, capable of measuring a speed difference smaller than a single kilometer per hour. The scientific world held its breath, expecting to finally confirm the foundation of their physics. The result was not just a disappointment, it was a profound shock. There was no shift, no interference pattern, no sign of an ether wind whatsoever. The experiment yielded a resounding null result. The speed of light was perfectly constant, regardless of the direction the apparatus was pointed or the time of year. It was as if the runner felt no wind at all, no matter how fast they ran. This should have been the moment the ether theory was discarded, a clear signal that this foundational concept was a phantom. Yet, the human mind, once invested in a beautiful idea, is remarkably resistant to contrary evidence. Instead of abandoning the ether, many prominent physicists contorted themselves to explain the null result. They proposed new, convoluted theories, such as the idea of ether drag, which suggested that the Earth somehow pulled the local ether along with it as it moved, eliminating any detectable wind. This was a classic case of saving the hypothesis by making it more complex and less testable, a desperate attempt to preserve a dying paradigm. This collective resistance created a significant delay, a period of stagnation where the revolutionary implications of the Michelson-Morley experiment were not fully embraced. It took the genius of a young patent clerk, Albert Einstein, to look at the same null result and see not a failed experiment, but a profound truth about the universe. In his 1905 paper on special relativity, Einstein started with two simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for everyone, regardless of their own motion. He didn't need to explain the Michelson-Morley result. He simply accepted it as a fundamental fact of nature. In doing so, he made the ether not just undetectable, but completely superfluous. Light, he showed, does not need a medium to propagate. It is a self-sustaining oscillation of electric and magnetic fields that can travel perfectly well through the void. The ghost of the ether was finally laid to rest, not by a new discovery, but by a courageous shift in perspective. The story of the ether is perhaps the ultimate cautionary tale in science. It demonstrates with painful clarity how preconceived notions and deeply held beliefs can act as a filter, distorting our interpretation of data and blinding us to the truth that is staring us in the face. The scientific method is designed to overcome this bias, but it is executed by fallible humans. Michelson and Morley provided the crucial evidence, but it was Einstein's willingness to question everything, to let go of the comforting idea of an absolute rest frame, that truly moved physics forward. This illusion teaches us that progress often requires more than just new data. It demands a revolution in thinking, a willingness to sacrifice elegant theories for messy, counterintuitive reality. The ghost of the ether reminds every scientist that the greatest obstacle to discovery is not always a lack of evidence, but sometimes a surplus of conviction. Imagine a night sky that is not a tapestry of dark velvet dotted with brilliant points of light, but a single, searing, blinding sheet of brilliance. Every single direction you look, your line of sight would eventually terminate on the surface of a star. The entire celestial sphere would glow with the ferocious intensity of the surface of the sun, rendering the universe a scorching, luminous oven where life could never exist. This is the terrifying, logical conclusion of a seemingly simple question, first posed by the astronomer Heinrich Wilhelm Olbers in the 19th century, though it had troubled thinkers for centuries before. If the universe is infinite, eternal, and filled with a uniform distribution of stars, then why is the night sky so profoundly dark? This puzzle, known as Olbers Paradox, presented a cosmic illusion so powerful that it fooled some of the greatest minds into concocting elaborate and ultimately incorrect explanations, all because they were trapped by an intuitive but flawed assumption about the nature of reality. The logic behind the paradox is deceptively simple and feels unassailable. Assume the universe is infinite in both space and time. It has always existed, and it is filled with an endless number of stars. In such a cosmos, no matter which direction you gaze, your line of sight should eventually land upon a star. It might be incredibly distant, but in an infinite universe, every single sightline ends at a stellar surface. Furthermore, because the universe has always existed, the light from even the most faraway stars would have had an infinite amount of time to travel across the void and reach our eyes. The result should be a sky that is everywhere as bright as the sun. The fact that we observe a dark night sky therefore seems to be a direct contradiction, a glaring observational fact that appears to falsify the idea of an infinite and eternal universe. This was the brilliant, inescapable trap of Olbers' paradox. Faced with this conundrum, scientists of the era proposed a series of clever but misguided solutions. One popular idea was that something must be absorbing the light from the most distant stars. Perhaps space was not a perfect vacuum but was filled with a faint, murky medium, a cosmic fog of dust and gas that gradually dimmed the light over immense distances, preventing the background from building up to an intolerable glare. This was a sensible, intuitive fix, but it contained a fatal flaw. If this absorbing material were truly soaking up all that starlight, it would itself heat up over time. According to the basic laws of thermodynamics, this interstellar fog would eventually reach thermal equilibrium and begin re-radiating the energy it absorbed, once again filling the sky with a uniform, blazing glow. The absorption theory merely delayed the problem, it didn't solve it. Another proposed solution was to suggest that the stars were not, in fact, distributed evenly. Maybe they were arranged in a hierarchical pattern or existed in isolated island universes, creating vast voids of empty space that would allow sightlines to escape into endless blackness. Yet others wondered if the light from the most distant stars simply hadn't had enough time to reach us yet, hinting at a universe with a finite age but not yet fully embracing the idea. These were all attempts to patch a leaking theoretical boat without realizing the entire vessel was built on a mistaken foundation. They were complex answers to a simple question, and they all missed the mark because they were trying to preserve the core assumptions of infinity and eternity. The true resolution to Olbers' paradox required nothing less than a complete cosmological revolution, a fundamental shift in our understanding of the universe's very origin and structure. The key that finally unlocked the paradox was the dual realization that the universe is both of a finite age and in a state of dynamic expansion. This monumental shift began with Edwin Hubble's observation of galactic redshifts in the 1920s, proving that galaxies are rushing away from each other, and was cemented by the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang. These discoveries provided the two crucial pieces of the puzzle. First, the universe is not infinitely old. It began approximately 13.8 billion years ago with a hot, dense initial state. This means that the light from stars beyond a certain distance has not had enough time to travel to us yet. Our observable universe is a finite bubble, and we cannot see anything beyond its horizon, no matter how powerful our telescopes. There are countless stars whose light is still en route and will be for billions of years to come. Second, and perhaps even more importantly, the expansion of the universe itself stretches the fabric of spacetime. This expansion has a profound effect on the light traveling through it. As this light journeys for eons across the expanding cosmos, its wavelength is stretched along with the space it moves through. This process, known as cosmological redshift, systematically shifts visible light into longer, redder wavelengths, and for the most distant sources, right out of the visible spectrum altogether and into the infrared and beyond. The energy of each individual photon of light is diminished by this stretching. So, not only is there a finite number of stars whose light has had time to reach us, but the energy from the most distant ones is dramatically reduced and reddened by the relentless expansion of the universe. This combination of a finite age and cosmic redshift solves Olbers Paradox completely. The sky is dark because the universe has a beginning, and because it is constantly stretching, cooling, and dimming the ancient light from its fiery birth. The story of Olbers Paradox is a stunning example of how a stubborn, apparent contradiction can act as a beacon, guiding scientists toward a deeper truth. For over a century, the dark night sky was a quiet, constant rebuke to the prevailing model of a static, eternal cosmos. It was an illusion that tricked thinkers into proposing increasingly complex band-aid solutions because they were unwilling to question their most basic assumptions. The ultimate resolution did not come from a minor adjustment, but from a total paradigm shift that redefined our place in the cosmos. It teaches a humbling and powerful lesson. Sometimes the most profound breakthroughs are not found by answering the questions we are asking, but by realizing that we have been asking the wrong questions all along. The darkness above is not a void to be filled with excuses, but a testament to a dynamic, evolving universe with a definitive story that began with a bang. While we often think of the cosmos as a realm of distant stars and galaxies, it constantly sends emissaries right to our doorstep in the form of cosmic rays, a relentless, invisible rain of high-energy particles that can play havoc with our most sensitive experiments. These are not rays of light, but actual subatomic fragments, protons, atomic nuclei, and other particles accelerated to nearly the speed of light by some of the universe's most violent events, like supernova explosions or the chaotic environments around black holes. When these tiny bullets from deep space slam into Earth's upper atmosphere, they shatter into a cascade of secondary particles that shower down upon the surface, penetrating even deep underground. For physicists hunting for the rarest events imaginable, this constant downpour creates a minefield of deception, where the signature of a mundane cosmic ray can be expertly disguised as a revolutionary discovery. This deceptive power was put on dramatic display in the quest to find proton decay, a process predicted by some grand unified theories that seek to merge the fundamental forces of nature. The idea is both simple and profound. What if the proton, the building block of all atomic nuclei and previously thought to be perfectly stable, could actually spontaneously fall apart after an immense timescale? To test this, scientists built enormous detectors like the famous one in a salt mine under Lake Erie, filling vast chambers with ultra-pure water and lining them with sensitive photodetectors. The concept was to wait patiently for the telltale flash of light that would be emitted if a proton inside one of those water molecules suddenly decayed. The expected signature was very specific, and when early experiments began to see signals that matched the prediction, excitement surged through the physics community. It seemed they might have cracked one of the universe's biggest secrets. The triumph, however, was short-lived. Upon meticulous review, researchers realized these flashes of light weren't coming from the peaceful decay of protons deep within the water tank. Instead, they were caused by muons, heavy, short-lived cousins of the electron that are created by cosmic rays hitting the atmosphere miles above. These muons, traveling at near light speed, could penetrate thousands of feet of rock to reach the underground detector. Once inside, they could interact with the water or the detector materials in ways that perfectly mimicked the anticipated signal of a dying proton. The cosmic rays had created a brilliant, convincing illusion, leading researchers down a false path and forcing a major revision of both experimental design and theoretical expectations. This experience was a humbling lesson that to find the extraordinary, you must first become a master of filtering out the ordinary. The challenge extends far beyond proton decay. Today, the same problem plagues the search for dark matter. The hypothetical particles that might make up this mysterious substance, such as WIMP, are expected to interact with normal matter only very rarely and very faintly. Their signature in a detector would be an incredibly subtle bump or scintillation of light, a whisper against a roar of background noise. Cosmic rays are a primary source of that roar. A stray muon or neutron from a cosmic ray shower can bounce through a detector and leave a signal that is virtually indistinguishable from that of a hypothetical dark matter particle. This forces scientists to take extreme measures. Modern dark matter experiments are now housed in the deepest underground laboratories on Earth, buried under a mile of solid rock that acts as a natural shield to filter out the majority of cosmic rays. They are built from materials meticulously selected for their ultra-low natural radioactivity, and they are surrounded by layers of sophisticated active veto systems, essentially God detectors that can identify and tag a passing cosmic ray particle so that any signal it creates in the main detector can be instantly discarded. This endless game of cosmic whack-a-mole, where every new layer of shielding and every new analysis technique is met with the universe's relentless creativity in creating false signals, is ironically one of the great engines of progress in experimental physics. The deceptive nature of cosmic rays doesn't just create problems, it forces innovation. It has driven the development of ever more sensitive particle identification software, groundbreaking shielding technologies, and statistical methods powerful enough to tease a single true signal out of billions of background events. Every illusion they present is a puzzle to be solved, making our detectors better and our conclusions more robust. The cosmic ray background is the ultimate sparring partner, constantly testing our experimental mettle and ensuring that when a genuine discovery is finally made, it will be so bulletproof that it will truly reshape our understanding of the universe. Peering into the deepest reaches of space requires more than just a powerful telescope. It demands a monumental act of faith, a belief that the faintest smudges of light captured over weeks of exposure are genuine windows into the early universe. This is the painstaking work behind iconic images like the Hubble Deep Field, where the space telescope was pointed at a seemingly empty patch of sky for days on end, gathering every precious photon to build a picture of breathtaking depth. The result is a crowded tapestry of thousands of galaxies, a core sample of the cosmos stretching back to its infancy. But nestled among these genuine cosmic landmarks are phantoms, faint, blurry objects that tease the promise of discovery but are, in reality, nothing more than clever mirages created by the very tools we use to see. These phantom galaxies represent a subtle and pervasive form of cosmic deception, one that challenges not just our instruments, but our ability to interpret what they show us. The sources of these illusions are as varied as they are frustrating. Some are born from the intricate optics of the telescope itself. A bright, well-defined star or galaxy can create faint, ghostly echoes in the image due to internal reflections within the complex array of lenses and mirrors. These artifacts, often called diffraction spikes or optical ghosts, can appear as new, separate objects lurking in the darkness. Other phantoms are the children of pure chance. The relentless hail of cosmic rays striking the telescope's digital sensor leaves behind sharp, bright streaks and spots that can, at a glance, be mistaken for a distant, point-like galaxy. Then there is the ever-present enemy of all deep space photography, noise. In the quest to detect the faintest objects, astronomers must amplify the electronic signal from their detectors, a process that also amplifies the random background fuzz of the instrument's own electronics. Occasionally, this random noise can coalesce into a pattern that looks suspiciously like a faint, extended galaxy, a digital Rorschach test set against the void. Perhaps the most humbling source of error comes from within our own cosmic backyard. Our Milky Way galaxy is filled with countless faint, low-mass stars called red dwarfs and brown dwarfs. These objects are so dim they are virtually invisible in most surveys, but in an ultra-deep field image, they can photobomb the view, appearing as faint, reddish smudges that are extremely difficult to distinguish from a truly distant, reddened galaxy. The challenge is a classic needle in a haystack problem, but where the haystack is the entire history of the universe, and some of the needles are actually just bits of straw. The consequences of being fooled by these phantoms are far more significant than a simple mislabeled picture. Census counts of galaxies in the early universe are a primary tool for testing our models of cosmic evolution. If a significant number of phantom objects are mistakenly counted as genuine high redshift galaxies, it could suggest that galaxies formed earlier and in greater numbers than our theories predict, potentially forcing a drastic and incorrect revision of our understanding of the Big Bang's aftermath. Conversely, if the software designed to filter out these false positives is too aggressive, it might discard real, faint galaxies, creating an illusion of a slower, more sedate period of galactic birth. The entire timeline of cosmic history could be skewed by what amounts to a few errant pixels in a massive digital image. Combating this illusion requires a dual approach of cutting-edge technology and old-fashioned human intuition. Sophisticated algorithms are trained to recognize the telltale signatures of different types of noise and artifacts. They can flag the perfectly straight lines of cosmic rays or the symmetrical patterns of optical ghosts. However, machines are not infallible. The final arbiter is often the trained eye of an experienced astronomer who can scrutinize a candidate object, compare its properties across different wavelengths of light, and make a judgment call based on a lifetime of pattern recognition. It is a slow, meticulous process of cosmic forensics, separating the true signal from the omnipresent noise. This ongoing battle against phantom galaxies is a powerful testament to the fact that in astronomy, seeing is not always believing. It is a rigorous process of verification, a reminder that every claim about the distant cosmos must first pass through the gauntlet of our own technological limitations and perceptual biases. Just when astronomers thought they had a handle on the strange signals the universe could produce, along came a phenomenon so bizarre and fleeting that it seemed to defy all explanation, creating a modern-day puzzle filled with false starts and tantalizing illusions. These are fast radio bursts, or FRB intense, millisecond-long blasts of radio waves that pack more energy than the sun emits in days, sometimes even months, all compressed into a blink of an eye flash that arrives without warning from the distant cosmos. Their discovery sent shockwaves through the astronomical community, not just because of their incredible power, but because they were so easy to dismiss as anything but real. In the constant struggle to separate cosmic truth from terrestrial trickery, FRBs became the ultimate test case, a lesson in how the most extraordinary discoveries are often hiding in plain sight, masquerading as mere glitches or human-made interference. The story of this cosmic deception begins in 2007, when astronomer Duncan Lorimer and his student David Narkevic were sifting through old archival data from the Parkes Radio Telescope in Australia, recorded back in 2001. They were searching for new pulsars, but instead they found something utterly anomalous, a single, colossal burst of radio energy that lasted just 5 milliseconds. It was like finding a single, deafening gunshot on a recording that was supposed to be of gentle rainfall. The signal was so strong and so brief that it screamed of being an artifact. The immediate and utterly reasonable assumption was that it was terrestrial interference, a glitch from a passing satellite, a burst from a military radar, or even a malfunction in the telescope's own electronics. The idea that such a powerful signal could come from deep space and last for such an impossibly short time seemed to violate common sense. The scientific community, rightly skeptical of such an extraordinary claim, met the so-called Lorimer burst with intense doubt. It was far easier to believe it was a phantom, a flaw in the data, than to accept it as a genuine window into a new and violent astrophysical process. This initial dismissal is a perfect example of the conservative nature of good science. The default position is always to assume the ordinary before invoking the extraordinary. Radio astronomy is particularly vulnerable to false positives. Our planet is awash in human-made radio signals from cell phones, Wi-Fi, aircraft, and satellites, all of which can create transient bursts that mimic cosmic events. This background chatter creates a constant game of cosmic or local that astronomers must play. For years after its discovery, the Lorimer burst remained an unsolved mystery, a ghost in the data that many tried to explain away. But then, something remarkable happened. Other astronomers began to find similar bursts in data from other telescopes around the world. The Arecibo telescope in Puerto Rico detected one, and then another, confirming that the phenomenon was real, repeatable, and undoubtedly of cosmic origin. The Lorimer burst was not a glitch. It was the first witness to an entirely new class of astronomical event, one that had been overlooked for years because it was too strange to be believed. This history created a fascinating duality in the field of FRB research, a delicate and ongoing tension between two equally vital scientific instincts, healthy skepticism and boundless open-mindedness. On one hand, the vast majority of candidate FRB signals detected by automated software do turn out to be terrestrial interference or instrumental noise. Filtering these out requires rigorous verification, often using multiple telescopes to see if the signal appears in the same place in the sky at the same time. This skeptical process is essential to avoid polluting the scientific literature with false claims. On the other hand, the story of the Lorimer burst is a permanent cautionary tale against being too skeptical, too quick to dismiss the anomalous. It reminds researchers that if a signal is strange, that is precisely the reason to investigate it more closely, not to ignore it. The greatest discoveries often lie just on the other side of what we currently believe is possible. This balancing act continues today as the mystery of FRBs deepens. We now know they come from far outside our galaxy, with some originating billions of light years away. Some are one-off events, while others, dubbed repeaters, flash again and again from the same location, allowing astronomers to pinpoint their home galaxies. The theories for their origins are as dramatic as the bursts themselves. They could be caused by incredibly magnetized neutron stars called magnetars having starquakes, or by the cataclysmic collision of dense objects like neutron stars and black holes. Some have even speculated, though with much less evidence, about artificial origins. Each new detection carries the ghost of that first Lorimer, burst the possibility that it might be a game-changing discovery or just another clever illusion from a universe that seems to take delight in keeping us guessing. The study of fast radio bursts is more than just a quest to explain a strange phenomenon. It is a live-action demonstration of the scientific method itself, a constant negotiation between doubt and wonder, where the courage to believe in a 5-millisecond anomaly can ultimately redefine our understanding of the cosmos. Of all the worlds in our solar system, none has captured our imagination quite like Mars. Its rusty red surface, polar ice caps, and day length so similar to our own have long made it the prime candidate for harboring life, or at the very least, the ingredients necessary for it. And at the heart of that search is the quest for liquid water, the one non-negotiable requirement for biology as we know it. For decades, our robotic emissaries have scoured the Martian landscape, and on several thrilling occasions, they have sent back data that seem to scream a single, electrifying message: we've found it. But time and again, these discoveries have turned out to be some of the most heartbreaking and instructive cosmic illusions in the history of exploration. Brilliant mirages that reveal just how cleverly a barren world can mimic the signs of vitality. One of the most compelling of these Martian tricks involves strange, dark features that appear to flow down steep slopes during the warmer months. From orbit, these recurring slope lineae, or RSL, look exactly what you would expect from seeping water. They darken and extend downhill when temperatures rise, then fade away when it gets colder, a behavior that perfectly matches a seasonal flow of briny liquid. The scientific community and the public were captivated. It seemed we were looking at direct evidence of liquid water actively shaping the Martian surface today. The implications for potential microbial life were staggering, but this beautiful story began to unravel upon closer inspection. While the pattern screamed water, other evidence was curiously absent. More powerful spectrometers couldn't detect the telltale chemical signature of water or hydrated salts at these sites. Furthermore, most of these flows were found on sun-baked slopes that were far too warm for even salty water to remain stable. It would instantly boil away in the thin Martian atmosphere. The leading explanation for the illusion is now far drier, but no less fascinating. Scientists now believe these features are likely caused by flows of granular material like sand and dust. The dark streaks are probably created by dry landslides triggered by the change in seasons, where darker subsurface material slides downslope, revealing itself against the brighter red surface dust. It's a completely arid process that perfectly mimics the appearance of a wet one. Another famous Martian mirage came from a different kind of sensor, one designed to listen for water hiding beneath the surface. The Mars Advanced Radar for Subsurface and Ionosphere Sounding, or MARSIS, instrument on the European Space Agency's Mars Express orbiter, uses radar pulses to probe deep underground. In the region near the South Pole, it detected an area that reflected these radar signals incredibly brightly. To radar scientists, a bright, sharp reflector like this usually means one thing on Earth: a boundary between rock and liquid water. The announcement of a potential 20-kilometer wide subsurface lake buried under the ice sent waves of excitement around the world. Yet, once again, the universe presented us with an illusion. Other researchers soon pointed out that the same bright radar signal could be created by other, less exciting materials. Certain types of clay, known as smectites, which are known to be abundant on Mars, are brilliant radar reflectors. So are deposits of metallic minerals. The simple, thrilling story of a hidden lake began to look more like a complex interplay of frozen geology. The lesson here is profound. A single line of evidence, no matter how compelling, is rarely enough to prove a claim as extraordinary as liquid water on another world. Remote sensing, for all its power, is inherently ambiguous. A spectrometer sees a chemical signature, a camera sees a shape, and a radar sees a reflection. Each one tells a part of the story, but it is only by combining them, by seeking multiple lines of corroborating evidence, that we can hope to see the full, true picture. These Martian water mirages are not scientific failures. They are masterclasses in how to do science correctly. They teach us the vital importance of tempering our excitement with rigorous skepticism. Each false positive forces us to re-examine our assumptions, to improve our instruments, and to refine our models. The search for water on Mars continues, now wiser and more sophisticated for having been fooled. We've learned that the red planet is a master of deception, capable of creating stunningly convincing facsimiles of hydrological activity through entirely dry means. This doesn't mean water isn't there. It simply means the universe is more creative and complex than we often anticipate. The pursuit continues, not with blind optimism, but with a resilient and determined curiosity, forever chasing the truth behind the illusion. Perhaps no other modern scientific announcement and subsequent retraction better illustrates the delicate, high-stakes nature of cosmological discovery than the dramatic story of the BICEP2 experiment. It's a tale that begins with one of the most elegant and ambitious theories ever conceived: cosmic inflation. This idea proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent an exponential growth spurt, inflating from a subatomic speck to something of macroscopic size faster than the speed of light. This radical theory wasn't just invented for its own sake. It beautifully solved several profound puzzles about the universe's large-scale smoothness and geometry. But like any good theory, it needed to make a testable prediction, and it offered a truly spectacular one. The violent, quantum-fueled process of inflation should have sent powerful shockwaves rippling through the fabric of spacetime itself, primordial gravitational waves. And these waves, in turn, would have left an indelible, faint imprint on the oldest light in the universe, the cosmic microwave background radiation. The specific signature to look for was a unique pattern of polarization in this ancient light, a swirling, curly pattern known as B-mode polarization. Finding it would be nothing less than a direct glimpse into the universe's first moment of existence, a discovery worthy of a Nobel Prize. The BICEP2 telescope, located at the brutally cold and dry South Pole, an ideal spot for such precise observations, was built for this singular purpose: to hunt for these telltale swirls. In March of 2014, the team made a blockbuster announcement that sent shockwaves through the global physics community. They declared they had done it. They had found the signal. The data, they said, provided the first direct evidence for primordial gravitational waves and, by extension, strong support for cosmic inflation. The press conference was electric. Headlines exploded around the world, and for a moment, it felt like a cornerstone of fundamental physics had been firmly laid into place. The potential implications were mind-bending. This wasn't just about confirming a theory of the early universe, but potentially shedding light on the dream of unifying gravity with quantum mechanics. The thrill of discovery was palpable. But in the world of cutting-edge science, extraordinary claims must withstand the scrutiny of the entire community, and the initial euphoria soon gave way to intense skepticism. Other researchers began to ask tough questions. The BICEP2 team had focused intently on a seemingly clean patch of sky, but had they adequately accounted for every possible foreground contaminant? The primary suspect was an ubiquitous and tricky component of our own galaxy: interstellar dust. Milky Way dust, when warmed by starlight, can itself emit polarized light, and it can create patterns that are incredibly difficult to distinguish from the primordial B-mode signal. It was a classic case of a cosmic illusion, where a local, mundane phenomenon perfectly mimics a grand, universal one. The BICEP2 team had used a model of galactic dust based on the best available data from the Planck satellite, but that data was preliminary. As the full Planck data was released and analyzed in a joint effort with the BICEP team, the sobering truth emerged. The swirling pattern they had seen was not the clean whisper from the dawn of time. It was overwhelmingly, perhaps entirely, caused by the polarized emission from this galactic dust. The signal was a mirage. The monumental announcement had been premature. The cosmological community had to perform a very public and humbling reassessment. This episode was not a failure of the scientists involved, who were operating at the very edge of what was technologically possible. Rather, it was a powerful object lesson in the immense challenges of modern cosmology. It underscored a fundamental truth: we are always observing the deep universe through a veil, a complex foreground of our own galactic neighborhood. Isolating the true cosmic signal requires an almost superhuman level of meticulousness, cross-checking across multiple experiments and wavelengths of light to isolate and subtract every last bit of local interference. The BICEP2 story remains a cautionary tale about the perils of confirmation bias and the absolute necessity of humility when interpreting the faintest whispers from the edge of reality. Our journey through cosmic deceptions now brings us closer to home, to the dark, frigid frontiers of our own solar system, where the hunt for new worlds has repeatedly led astronomers down paths that end not in discovery, but in disillusionment. For over a century, the tantalizing possibility of a large, undiscovered planet lurking in the solar system's outskirts has captivated both scientists and the public, fueling a quest that has been as much about perseverance as it has been about patience. This search, conducted through painstaking surveys of the star-strewn sky, is a meticulous process of comparing photographic plates or digital images taken nights or weeks apart, looking for one faint point of light that has moved against the fixed background of distant stars. It is grueling, eye-straining work, and it is a process perfectly designed to produce some of the most compelling and frustrating illusions in all of astronomy: the phantom planet. The most famous of these spectral worlds is, of course, Planet X, a hypothetical giant planet proposed to explain perceived irregularities in the orbits of Uranus and Neptune. While the search for Planet X famously led to the discovery of Pluto in 1930, the original impetus was based on a mirage. The orbital anomalies that prompted the search were later revealed to be mere artifacts of imperfect data. More precise measurements showed that the orbits of the outer planets were exactly as predicted by Newtonian gravity, with no need for an additional perturbing body. Yet the idea refused to die, periodically resurrected by new generations of astronomers who believed they saw faint gravitational whispers in the motions of distant objects in the Kuiper belt. Each time, more advanced surveys and more sophisticated orbital calculations have chipped away at the possibility, shrinking the allowable space where such a planet could hide until its existence now seems increasingly unlikely. The original Planet X was a classic case of a theory outstripping the data, a mathematical ghost born from measurement error and the powerful human desire to find patterns, even when none exist. Modern surveys, armed with digital cameras and automated computer algorithms, have not eliminated this problem. They have simply changed its form. Projects like the Dark Energy Survey or dedicated trans-Neptunian object searches use software to scan millions of telescope images, flagging any object that moves between exposures. This automation is essential for processing the immense volume of data, but it introduces new avenues for deception. A cosmic ray strike on the camera's sensor can create a bright, sharp pixel that appears in one image but not the next, perfectly mimicking a moving object. More insidiously, two faint stars or distant galaxies can align by chance in such a way that the software stitches their light together into a single, artificial point source that appears to shift position. Even something as simple as a software bug in the motion tracking algorithm can create a cascade of false positives, generating entire families of phantom planets that exist only as lines of errant code. Perhaps the most humbling lesson from these false detections is how they reveal the subtle ways our own expectations can bias the search. When an astronomer is actively hoping to find a new planet, that desire can subconsciously influence the interpretation of ambiguous data. A faint, blurry smudge at the very limit of the telescope's resolution might be dismissed as noise under normal circumstances, but in the heat of the hunt, it can be re-examined, enhanced, and perhaps even willed into being as a potential candidate. This psychological trap is why the scientific method places such a heavy emphasis on independent verification. A claim of a new planet is only taken seriously when multiple telescopes, often operated by different teams who have no stake in the original discovery, can re-observe the same patch of sky and confirm the object's existence and orbit. This process of collaborative scrutiny is the essential filter that separates true discovery from wishful thinking, ensuring that every new world we add to our maps is a genuine resident of our solar system, and not just a fleeting trick of the light or a glitch in the machine. One of the most fundamental assumptions in all of cosmology is the idea that on the very largest scales, the universe is homogeneous and isotropic. This cosmological principle suggests that if you were to zoom out far enough, the cosmos would look roughly the same in every direction and from every location, a vast, evenly distributed cosmic web of galaxies and dark matter with no special place or preferred direction. It's a beautiful, democratic idea that forms the bedrock of our standard model of the universe, from the equations of general relativity to our interpretations of the Big Bang. But what if this very uniformity is itself an illusion, a trick of perspective born from our own limited vantage point? The truth is, when we look out into the depths of space, we don't see a perfectly smooth soup. We see a landscape of breathtaking complexity, with galaxies huddled together in immense clusters, strung along filaments that stretch for hundreds of millions of light years, and separated by terrifyingly empty voids so vast they defy human comprehension. This grand structure creates a powerful deception, where local concentrations and absences of matter can trick us into seeing patterns and anomalies that challenge the very notion of a uniform cosmos. A perfect example of this cosmic sleight of hand is the ongoing debate surrounding what's known as the KBC void, named for the scientists Keenan, Barger, and Cowie who proposed its existence. Their analysis suggested something startling, that our own Milky Way galaxy resides in a region of space that is significantly emptier than the cosmic average. We are not in a special place, but we might be in a strangely sparse one, a vast underdensity, a cosmic bubble hundreds of millions of light years across where the density of galaxies is noticeably lower than in the universe at large. If true, this would have profound implications. Many of our measurements of cosmic expansion and the properties of dark energy rely on the assumption that we are typical observers in a typical region of space. If we are actually sitting in a giant void, it could mean that the apparent acceleration of the universe's expansion isn't a global property driven by dark energy, but a local illusion. The lower density inside our bubble would mean less gravitational pull holding us back, making it seem like galaxies outside our void are rushing away faster than they truly are. much like a boat in a gently sloping river, will seem to accelerate as it moves from a calm eddy into the faster current. The controversy lies in determining whether the KBC void is a real physical structure or a classic case of a selection effect, a bias introduced by the way we collect our data. When astronomers map the large-scale structure of the universe, they are not just taking a simple photograph, they are conducting a complex census, and any census can have blind spots. Certain telescopes can only see galaxies of a certain brightness, and dust within our own galaxy can obscure our view of specific regions of the sky, creating artificial gaps in the data. The methods used to estimate galactic distances also have inherent uncertainties. Critics of the void hypothesis argue that what looks like a giant underdensity could simply be a consequence of these observational limitations. We might be misinterpreting an incomplete map as evidence for a grand cosmic emptiness, building a giant theoretical bubble out of the places we haven't been able to look yet. This debate is a magnificent demonstration of science in action, where a single anomalous observation forces us to meticulously question our methods, our instruments, and even our most foundational principles. This illusion of cosmic homogeneity teaches us a crucial lesson about perspective. We are, by necessity, fixed observers. We have only one window into the universe, and it is located right here. This unique vantage point is both our greatest gift and our biggest liability. It allows us to build a deep and detailed understanding of our immediate cosmic neighborhood, but it also means we can never be entirely sure that our local view is representative of the whole. The grand filaments and voids we see could be giving us a distorted sense of the cosmos's true texture, making us wonder if the apparent smoothness is just an average that emerges over distances so immense we cannot yet comprehend them. It is a humbling reminder that to truly understand the universe, we must constantly strive to see beyond our own backyard, to compare our maps with those that might be made by hypothetical astronomers in a distant galaxy cluster, and to remember that the cosmos has a way of appearing orderly only until we look closely enough to see the beautiful, complicated, and deceptive chaos within. For a brief, captivating moment in the history of astronomy, the universe seemed poised to reveal a mirror image of itself, a shadow cosmos built not from the ordinary matter we know, but from its perfect opposite. The theoretical possibility of entire galaxies made of antimatter is one of the most electrifying ideas ever conceived. Antimatter is not science fiction. It is a very real substance where particles carry the opposite electrical charge of their normal counterparts. An antiproton is negatively charged while a positron or anti-electron is positive. The most dramatic property of antimatter is what happens when it meets normal matter. They annihilate each other in a spectacular flash of pure energy, converting their mass into intense gamma-ray radiation. This dazzling physics led some theorists to wonder, if the universe can make galaxies of matter, why not galaxies of antimatter? Perhaps, they suggested, during the violent asymmetry of the Big Bang, vast regions of space were seeded with antimatter instead, and these domains could have collapsed into stars, planets, and even potential life made entirely of anti-atoms. It was a concept of breathtaking elegance and symmetry, a universe in perfect balance. The hunt for these phantom galaxies then became a race to find the one unmistakable signature that would betray their existence, the telltale glow of annihilation. If an entire galaxy were made of antimatter, its border would be a cosmic war zone, a permanent frontier where drifting clouds of anti-hydrogen from the antimatter galaxy would inevitably mingle with normal hydrogen atoms from our own galactic neighborhood. This contact would trigger a continuous cascade of mutual destruction, producing a specific and potent background hum of gamma rays with a very precise energy signature. For a time, the data seemed to offer a glimmer of hope. Early observations of the cosmic gamma-ray background did show an unexplained excess, a faint whisper of energy that could, with a generous interpretation, be seen as evidence for these annihilation frontiers. Furthermore, the detection of a few antiprotons in cosmic rays particles that rained down on Earth from deep space added more fuel to the speculative fire. Could these be fragments, tiny messengers from a distant anti-galaxy, proof that such mirror worlds were not just possible but real? This is where the universe's talent for deception shone through. The initial excitement was a classic case of a beautiful theory being assaulted by ugly facts. As our observational technology advanced, particularly with powerful instruments like the Fermi Gamma-Ray Space Telescope, astronomers were able to map the gamma-ray sky with unprecedented sensitivity and resolution. They searched intently for the specific, sharp emission lines that are the unique fingerprint of proton-antiproton annihilation. The result was a profound silence. The sky was simply too quiet. There were no concentrated sources of this radiation, no glowing boundaries between matter and antimatter domains that would indicate the presence of even a single antimatter galaxy, let alone vast regions of them. The mysterious gamma-ray background that had initially sparked excitement was eventually explained by more mundane sources, like the collective emission from distant pulsars and active galactic nuclei. The few antiprotons detected in cosmic rays also found a more ordinary explanation. They are now understood to be secondary products, created when high-energy normal matter cosmic rays collide with interstellar gas and dust, a process that can forge antiparticles in the aftermath of the collision. The grand mirage of the Antimatter Galaxy is a powerful lesson in the scientific dialogue between imagination and evidence. It demonstrates how a mathematically elegant and philosophically satisfying idea can captivate our minds and create a compelling illusion of truth. The human brain is naturally drawn to symmetry and balance, and the concept of a universe equally divided between matter and antimatter fulfills that deep aesthetic craving. This desire for elegance can sometimes create a kind of perceptual bias, where we unconsciously overweight ambiguous data that supports the beautiful theory and discount evidence that contradicts it. The eventual dismissal of antimatter galaxies was not a failure of science, but its greatest success. It was a process of patiently allowing empirical evidence, gathered through increasingly powerful telescopes, to discipline and refine our wildest speculations. It forced theorists to develop more nuanced models for why our universe appears to be made almost entirely of matter, a puzzle that remains one of the greatest unsolved problems in physics. This episode ultimately fostered a healthier, more productive relationship between theory and observation, reminding us that while elegance can guide us to a hypothesis, only hard, uncompromising data can ever confirm it. Of all the relics left behind by the Big Bang, none is more precious or revealing than the cosmic microwave background radiation. This is the oldest light in the universe, a faint, cold glow that fills every corner of the sky, a snapshot of the cosmos when it was a mere 380,000 years old, finally cool enough for light to travel freely. For cosmologists, this radiation is a sacred text. Its tiny temperature variations minute fluctuations of mere millionths of a degree, encoding the secrets of the universe's birth and its ultimate fate. Mapping these fluctuations with exquisite precision has been one of the great triumphs of modern science, confirming our standard model of cosmology with stunning accuracy. But within this near-perfect map, a few stubborn anomalies have stood out, strange and seemingly inexplicable features that have tempted scientists with the most revolutionary of explanations, only to reveal themselves as some of the most profound cosmic illusions of all. The most famous of these enigmatic features is known as the cold spot. Discovered in the data from the Wilkinson Microwave Anisotropy Probe, this region of the sky, located in the constellation Eridanus, is significantly colder than the surrounding cosmic background, a vast, chilling blotch on the infant universe's face. Its size and coldness were so statistically unusual, so far outside the expected random distribution of temperature variations, that it demanded an exotic explanation. The standard model of cosmology, which beautifully explains most of the universe's properties, had no ready answer for this particular anomaly. This vacuum of understanding became a fertile ground for some of the most spectacular and mind-bending theories in physics. One captivating hypothesis proposed that the cold spot was not a feature of our universe at all, but a bruise, a literal collision with another universe. In the controversial multiverse interpretation of eternal inflation, our cosmos is just one bubble in a vast, frothing foam of universes, each with its own physical laws. Theorists suggested that if another bubble universe had, in the distant past, bumped up against our own, the energy released at that boundary could have left a specific, circular imprint on the cosmic microwave background, a cold scar exactly like the one we observed. It was a breathtaking idea, the first empirical evidence for a reality beyond our own cosmos. Other, less extreme but equally exotic explanations were also put forward, including cosmic textures. These would be defects in the fabric of space-time, topological knots formed during the universe's early phase transitions, which could create specific gravitational signatures that would cool the background radiation in a particular way. For a time, the cold spot was more than just data. It was a symbol of the frontier, a beacon for those who believed our current understanding of physics was merely the tip of a much deeper, weirder iceberg. It represented the thrilling possibility that we were on the verge of a paradigm shift as profound as the one sparked by the discovery of the cosmic microwave background itself. But science at its best is a self-correcting process. Extraordinary claims require not just extraordinary evidence, but the relentless elimination of all ordinary explanations. As more powerful telescopes, most notably the Planck satellite, mapped the cosmic microwave background with even greater sensitivity and resolution, the tide began to turn. The cold spot was still there, but its mystique began to fade under a wave of more sober analysis. The most likely explanation for the anomaly turned out to be a classic case of cosmic chance, amplified by a subtle observational effect. When cosmologists ran massive computer simulations of the universe based on the standard model, they found that while a cold region of that exact size and significance was extremely rare, it wasn't impossible. In a universe that is, by its very nature, a tapestry of random quantum fluctuations stretched to cosmic scales, statistical outliers are not just expected, they are inevitable. If you roll a dice enough times, you will eventually get a long string of sixes. The cold spot, for all its grandeur, might simply be that string of sixes, a rare but natural fluctuation in an otherwise random field. Furthermore, a more prosaic culprit emerged: foreground effects. Our view of the pristine cosmic microwave background is always filtered through the messy contents of our own galaxy and beyond. Some researchers proposed that the cold spot could be explained by a vast, but previously undetected, supervoid, an immense region of space with a significantly lower density of galaxies. While light passing through such a void wouldn't be cooled in the traditional sense, the complex interplay of general relativity and the universe's expansion could create a specific dimming effect that mimics a temperature drop in the background radiation. The story of the cold spot is a masterclass in scientific humility. It demonstrates the powerful tension between two essential forces in research: the bold, imaginative leap that dares to propose radical new ideas, and the careful, meticulous scrutiny that tests those ideas against reality. The initial, exotic interpretations were not foolish. They were a necessary and creative response to an intriguing puzzle, but they were ultimately tempered by Occam's razor, the principle that the simplest explanation, the one that requires the fewest new assumptions, is usually correct. In this case, the simplest explanation was that we were seeing a combination of a statistical fluke and a large, empty region of space, not a window into the multiverse. This doesn't make the cold spot any less fascinating, but it does reframe its significance. It is no longer a potential revolution, but a powerful reminder of the constant vigilance required to interpret the universe's signals. It teaches us that the most alluring whispers from the edge of physics are often just the universe murmuring to itself in a language of random probability, and that the true challenge is not just in hearing the murmur, but in understanding the difference between a cosmic secret and cosmic static. We often picture our solar system as a grand, intricate, and perfectly balanced clockwork mechanism, with planets tracing out their elliptical orbits with such reliable precision that we can predict their positions thousands of years into the future. This vision of cosmic harmony is deeply comforting, suggesting a universe governed by orderly, predictable laws where once a planet finds its path, it remains there, stable and secure for all eternity. This perception, however, is one of the most persistent and dangerous cosmic illusions. The reality, as revealed by the unforgiving mathematics of chaos theory, is that our solar system and all planetary systems are fundamentally chaotic, seething with unpredictable interactions where the slightest gravitational nudge can, over immense timescales, lead to consequences as dramatic as planetary collisions or the violent ejection of a world into the cold depths of interstellar space. The illusion of stability is a trick played by our short human lifespans. We see only a single, frozen frame of a billion-year movie and mistake it for the entire peaceful story. This understanding didn't come from simply staring at the sky with more powerful telescopes. It was born from the marriage of theoretical physics and raw computational power. For centuries, the n-body problem, calculating the motions of multiple objects all gravitationally influencing each other, proved mathematically intractable for more than two objects. While physicists could write down the equations of motion for the solar system, they couldn't solve them exactly. This forced them to rely on approximations, treating planetary orbits as isolated two-body problems between each planet and the Sun, with the gentle tugs from other planets treated as minor, predictable perturbations that would average out over time. This simplified model created the powerful illusion of long-term stability, suggesting that the solar system we see today is essentially the same one that has existed for billions of years and will persist for billions more. It was a beautiful, orderly, and completely misleading picture. The cracks in this serene facade began to show with the help of some of the world's most powerful computers. Scientists began running numerical simulations that could finally model the full, chaotic gravitational dance of the planets, projecting their motions not just for millions but for billions of years. The results were startling. While the giant outer planets like Jupiter and Saturn exhibit a relatively stable rhythmic resonance, the inner solar system, home to smaller, closer-packed worlds, was revealed to be a potential powder keg of gravitational instability. The prime subject of this disturbing revelation was the innermost planet itself, Mercury. Its small size and elongated orbit make it particularly vulnerable to the subtle, cumulative gravitational tugs from its larger neighbors, especially Jupiter. Early, simplistic models had suggested its orbit was stable, but more sophisticated simulations revealed a faint but real possibility that over the next 5 billion years or so, Jupiter's influence could gradually pump up the eccentricity of Mercury's orbit, making it more and more elliptical. This path leads to potential catastrophe. A wildly eccentric Mercury could one day cross the orbit of Venus, setting the stage for a close gravitational encounter that could fling the small planet on a chaotic path across the inner solar system. The simulations paint a dramatic and terrifying picture of what could follow: a chance collision with Venus, Earth, or even the Sun, or a close pass that sends Mercury careening out of the solar system entirely as a rogue planet. Even more astonishingly, this Mercurian chaos could destabilize the entire inner solar system like a game of gravitational billiards, potentially leading to a collision between Earth and Mars. While the probability of such an extreme outcome is low, perhaps only around 1%, its very possibility is what shatters the illusion. It proves that the solar system is not a predetermined, immutable clockwork, but a dynamic and potentially volatile system whose long-term fate is inherently unpredictable. This discovery forces a profound humility upon us. It teaches that in any complex, interacting system, whether it's a family of planets, Earth's climate, or even the global economy, the assumption of perfect predictability is a dangerous fantasy. Tiny, immeasurable changes in the initial conditions, a concept famously known as the butterfly effect, can amplify over time to produce wildly different outcomes. We can run 1,000 simulations of the solar system's future and get 1,000 slightly different results. We can know the range of possibilities, but we can never know with absolute certainty which path reality will take. The deceptive stability of our celestial neighborhood is ultimately a testament to the incredible power of computational science. It was only by building a digital twin of our solar system and letting it run fast forward through eons we cannot physically observe that we were able to peer through the illusion and glimpse the true, chaotic, and awe-inspiring nature of cosmic mechanics. Standing beneath a sky strewn with countless stars, it's perhaps the most natural question in the world: is anybody else out there? With hundreds of billions of galaxies, each containing hundreds of billions of stars, the numbers seem to shout a resounding yes. The sheer statistical probability feels overwhelming, a cosmic imperative that life must have sparked elsewhere. And yet, when we train our most powerful instruments on the heavens, listening for a whisper, a signal, any sign of another civilization, we are met with a profound and unsettling silence. This contradiction between the high probability of extraterrestrial intelligence and the complete lack of any evidence for it is known as the Fermi Paradox, named for the physicist Enrico Fermi, who famously asked, "Where is everybody?" This silence isn't just an absence of data. It feels like a cosmic riddle, and it may be one of the most sophisticated illusions the universe has ever presented us with. A trick played not on our eyes, but on our expectations and our deepest assumptions about reality. The illusion of this great silence stems from a deceptively simple calculation. The Drake equation, formulated by astronomer Frank Drake, provides a framework to estimate the number of communicative civilizations in our galaxy. It multiplies a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction where life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such a civilization lasts. The problem is that for most of these factors, we only have one data point: Earth. We are quite literally guessing. We plug in optimistic numbers based on our own existence and get an answer that the galaxy should be teeming with life. But what if we've profoundly overestimated the probabilities? The first layer of the illusion is that we assume the steps from non-life to a spacefaring civilization are common, even inevitable given enough time. But each of those steps, from the formation of the first self-replicating molecule to the development of multicellular complexity, to the rise of a technological species, could be a monumental, universe-rare fluke. The silence might not be a paradox at all, but simply a reflection of the fact that we are astonishingly, uniquely alone. This line of thinking leads directly to one of the most haunting proposed solutions to the Fermi paradox, the concept of the Great Filter. This is the idea that somewhere along the evolutionary path from sterile planet to interstellar civilization, there exists a barrier, a step or event that is so improbable or so dangerous that it effectively prevents almost all life from progressing beyond it. The terrifying question is not if the Great Filter exists, but where it lies in our own timeline. If it exists in our past, perhaps the origin of life itself, or the jump to complex eukaryotic cells, then it could explain the silence. We are the rare, lucky ones who made it through, and the galaxy is empty because no one else could. This is a comforting thought in its own way, but the more dreadful possibility is that the Great Filter awaits us in our future. Perhaps every advanced civilization, upon reaching a certain technological level, inevitably discovers the means of its own destruction, whether through nuclear war, environmental collapse, or a technology we haven't even conceived of yet, like a runaway artificial intelligence. In this scenario, the silence is not an illusion of rarity, but a cemetery quiet, the aftermath of a universal inevitability that we ourselves are rapidly approaching. Yet, even this chillingly elegant solution could itself be a form of cosmic deception, an illusion born from our own limited perspective. The Great Filter is a profoundly human-centric idea, born from our linear view of progress and our own historical anxieties. It assumes that the path to intelligence follows a single, predictable trajectory similar to our own, and that the challenges we face are the same challenges every civilization must overcome. This is an enormous assumption. A truly alien intelligence might not develop technology in the way we have. Its priorities might be entirely different. Perhaps it explores the universe through consciousness or biological adaptation, not radio waves and rockets. Their civilization might be so utterly alien to our conception that we wouldn't even recognize their signals or their artifacts if we stumbled upon them. We are searching for a reflection of ourselves in the cosmos, and the silence might simply mean that our mirror is too small. The real filter might not be a physical barrier, but a perceptual one, a failure of our own imagination to conceive of forms of existence beyond our own. Beyond the philosophical, there are deeply practical limitations creating the illusion of silence. Our search for extraterrestrial intelligence, or SETI, is astonishingly limited in both time and space. We have only been seriously listening for a few decades, a mere blink of an eye on cosmic timescales. A civilization might broadcast for 1,000 years, but if that window doesn't overlap with the minuscule slice of time during which we have our ears cupped to the sky, we would miss it completely. Furthermore, we've only sampled a tiny fraction of the possible frequencies and a negligible number of star systems. It is the equivalent of taking a single cup of water from the ocean and, upon finding no fish, concluding the entire sea is barren. Our technology is also primitive. An advanced civilization might not use primitive radio waves at all, instead communicating through neutrinos, gravitational waves, or some other medium we are only beginning to understand or cannot yet detect. The silence, therefore, is not evidence of absence, but a testament to the infancy of our search and the sheer, mind-numbing vastness of the cosmic haystack in which we are looking for a needle that might not even exist, or might be hiding in a strand of hay we never thought to check. If black holes are the universe's ultimate vacuum cleaners, relentlessly sucking in everything that crosses their event horizon. Then their theoretical opposite would be cosmic fire hydrants, spewing out matter and energy in a violent, one-way torrent that nothing can enter. This bizarre hypothetical object is known as a white hole, and it represents one of the most tantalizing and persistent phantoms in all of theoretical physics. The idea emerges not from wild speculation, but from the cold, elegant mathematics of Einstein's theory of general relativity. The equations that describe a black hole are, in a sense, time-symmetric. If you were to mathematically reverse the direction of time in the solution for a black hole, you would get a white hole, a region of space-time from which matter and light can only emerge but never return. It's a beautifully symmetrical concept, a perfect cosmic balance to the darkness of a black hole. For decades, this mathematical possibility has captivated theorists, offering a potential explanation for the Big Bang itself, or even a speculative exit from a black hole into another universe. But this elegant symmetry has also created a powerful and enduring cosmic illusion, a siren song that has led astronomers on a fruitless hunt for an object that almost certainly does not exist. The allure of this mirage is easy to understand. The universe is full of incredibly violent, transient, and energetic explosions that we struggle to explain. When astronomers began detecting gamma-ray bursts in the late 1960s, brief, incomprehensibly energetic blasts that appeared randomly across the sky, the mystery was profound. Here were events that, for a few seconds, could outshine every star in 100 billion galaxies combined. In the absence of a clear explanation, the exotic nature of white holes made them a compelling, if fringe, candidate. Perhaps, some theorists suggested, a white hole eruption was a singular event, a cosmic burp where a black hole in another universe or another time suddenly and violently reversed its nature, expelling all the matter it had ever consumed in a cataclysmic flash. Other mysterious events, like certain ultra-high-energy cosmic rays or inexplicable radio bursts, were also momentarily considered through this exotic lens. The white hole hypothesis was a classic example of reaching for an extraordinary explanation for an extraordinary phenomenon. However, the relentless progress of observational astronomy has steadily drained the white hole concept of its plausibility. One by one, those mysterious transient events found far more conventional, if still astounding, explanations within the standard laws of physics. Gamma-ray bursts are now understood to be the birth cries of black holes themselves, formed during the hypernova collapse of massive stars or the mergers of incredibly dense objects like neutron stars. The incredible energy they release comes from the physics of relativistic jets and accretion disks, not the violation of causality. The second law of thermodynamics, which dictates that entropy, the disorder of a system, must always increase, presents an even more fundamental problem for white holes. A white hole spontaneously appearing and spewing out ordered, low-entropy matter would seem to violate this most sacred of physical laws, effectively allowing time to run backwards on a macroscopic scale. While the equations of general relativity might permit such an object, the universe we observe appears to have a profound and unwavering arrow of time that white holes would directly contradict. The story of the white hole mirage is ultimately a cautionary tale about the dangerous allure of mathematical beauty over physical reality. It illustrates the critical distinction between something being mathematically possible and physically plausible. The universe is not obligated to actualize every solution that emerges from our equations, especially those that require the reversal of time or the violation of deeply established thermodynamic principles. The hunt for white holes has pushed astrophysicists to better understand the true nature of cosmic explosions. forcing them to develop more robust models that operate within the known laws of physics. In doing so, it has strengthened our understanding of the universe, not by discovering a new type of object, but by conclusively showing that the most awe-inspiring events we witness do not require magic or mystery. They simply require us to apply the known laws of physics to their most extreme and magnificent limits. The white hole remains a fascinating ghost in the machine of general relativity, a testament to the power of human imagination, but also a permanent reminder that the universe often prefers messy reality to perfect symmetry. Just as the concept of white holes demonstrates the allure of mathematical symmetry, another powerful idea has captured the imagination of cosmologists seeking to explain an even grander mystery: the accelerating expansion of the universe. This observed phenomenon, which earned its discoverers a Nobel Prize, tells us that something is counteracting the relentless pull of gravity on cosmic scales, pushing galaxies apart at an ever-increasing rate. The simplest explanation, the one that requires the fewest new assumptions, is to reintroduce a fudge factor that Albert Einstein himself once called his greatest blunder, the cosmological constant. This represents a constant energy density inherent to the vacuum of space itself, a steady, unchanging pressure that drives the acceleration. It's an elegant, minimalist solution. But what if dark energy isn't constant? What if it's a dynamic force changing over the lifetime of the cosmos? This captivating possibility is known as quintessence, a name harkening back to the ancient Aristotelian concept of a fifth element beyond earth, air, fire, and water. Quintessence proposes that dark energy is not a static property of empty space but a dynamic field, much like the Higgs field, that permeates the universe and whose energy density can evolve over time. The theoretical appeal of quintessence is immense. It offers potential solutions to some of the most nagging fine-tuning problems in cosmology. The observed value of the cosmological constant is famously and inexplicably tiny compared to theoretical predictions from quantum physics. A dynamic field could have started with a higher value in the early universe and then naturally decayed to the minuscule level we observe today, making its current value less of a bizarre coincidence. Furthermore, by allowing the strength of dark energy to change, quintessence could potentially reconcile the stubborn tension between measurements of the universe's expansion rate taken from the early universe and those taken from the nearby modern universe. This flexibility makes quintessence a seductive idea, a theoretical Swiss Army knife that seems capable of solving multiple problems at once, and herein lies the danger. This very flexibility makes quintessence incredibly difficult to falsify. With enough free parameters knobs to twist and dials to turn, a sophisticated quintessence model can be tuned to fit a wide range of observational data almost perfectly. This creates a profound and subtle cosmic illusion, the phantom energy of a field that might not actually be there. The risk is one of overfitting. Imagine you have a handful of data points scattered on a graph. You can draw a simple, smooth line that goes generally near most of them, which is what the cosmological constant does. Or you can use a complex, wiggly function that threads through every single data point perfectly. At first glance, the perfect fit seems superior, but if those data points have even tiny errors or uncertainties, that complex function isn't describing the underlying truth, it's merely describing the noise. It's fitting the ghosts in the machine rather than the machine itself. This is the trap of quintessence. By adding complexity, it can appear to provide a better fit to certain datasets, creating the compelling illusion that we are seeing evidence for a dynamic field. Early analyses of supernova data, for instance, sometimes showed slight deviations from the predictions of a pure cosmological constant. These hints, these faint whispers in the data, were enough for some researchers to claim evidence for quintessence. suggesting the field was evolving in a specific way. The excitement was palpable as it promised a window into entirely new physics beyond Einstein's cosmological constant. However, as is so often the case in cosmology, the initial excitement gave way to a more sober and rigorous reality check. When independent teams analyzed larger, more precise datasets from different sources combining supernova with maps of the cosmic microwave background and the large-scale structure of galaxies, the evidence for these deviations began to evaporate. The supposed signals for a dynamic quintessence field were not consistently found across all observations. What looked like a detectable evolution in one dataset became statistically insignificant when combined with others. The best fit to the full body of evidence consistently pointed back to the simplest explanation: a cosmological constant. The phantom energy of quintessence faded under the harsh light of cross-verification, revealing itself to be a mirage born from the statistical uncertainty inherent in measuring the distant universe. This episode serves as a critical lesson in the principle of parsimony, often known as Occam's razor. When faced with multiple explanations for a phenomenon, the one that makes the fewest assumptions is often correct. Cosmology, at its heart, is a forensic science trying to reconstruct the history of the universe from fragmentary evidence. It is all too easy to be seduced by a more complex and seemingly explanatory story, but the true path to understanding lies in a stubborn commitment to simplicity and a relentless demand for independent, corroborating evidence from multiple cosmic sources. Galaxies are not the isolated, serene island universes they were once thought to be. They exist in a state of constant gravitational negotiation, often leading to violent and transformative encounters. These galactic mergers are some of the most dramatic events in the cosmos, and while they forge breathtaking new structures, they are also masterful creators of cosmic illusions. When two galaxies swing past each other in a close gravitational dance, they don't simply crash directly. Their mutual gravity acts like a titanic tidal force, stretching and pulling stars and gas out into vast, sweeping streamers that can extend for hundreds of thousands of light years. These magnificent structures, known as tidal tails, are the most common source of deception. To an astronomer surveying the sky and cataloging objects, a bright, condensed knot of stars at the tip of a tidal tail can appear, at a glance, to be a perfectly respectable dwarf galaxy. It has stars, it has a gravitational binding, it seems to be a distinct entity. This misclassification is more than just a clerical error. It leads to a completely flawed understanding of how dwarf galaxies form and how matter is distributed throughout the universe. If we mistakenly count these tidal dwarfs as primordial galaxies, we are effectively counting cosmic phantoms, creating an illusion of a population of small galaxies that doesn't actually exist in the way our models predict. This skews our entire census of galactic evolution, suggesting a different history for the universe than what truly occurred. The deception doesn't stop with phantom galaxies. The sheer violence of a galactic collision triggers monumental bursts of new star formation as clouds of gas are violently compressed. These starbursts can be so intense that they briefly outshine the combined light of every other star in the merging galaxies. To a distant observer who catches this event at its peak, the entire system can look like a single, bizarre, and incredibly luminous object. In the early days of radio astronomy, before we understood the dynamics of mergers, some of these colliding galaxies were misclassified as entirely new types of celestial objects. Their unusual, distorted shapes and spectacular energy output didn't fit neatly into the existing categories of spiral or elliptical galaxies. It was only through painstaking analysis and the development of more sophisticated computer simulations that astronomers realized they were not looking at a strange, isolated monster, but a fleeting, albeit spectacular, phase in the life cycle of perfectly normal galaxies. This realization was crucial. It taught us that to understand what we are seeing, we must understand the context. A single snapshot in time is not enough. We must deduce the history of the object and its likely future. A galaxy that appears peculiar and unique might simply be caught in a brief, traumatic moment of a much longer and more common narrative. This highlights a fundamental shift in how we practice astronomy today. The field has moved from simply cataloging static objects to unraveling dynamic processes. We now understand that galaxies are not frozen sculptures but evolving characters in a cosmic story, and their interactions are the plot twists that drive that story forward. The illusions born from galactic cannibalism are a powerful reminder that context is everything. A lone object in a telescope's field of view is just a data point. Its true meaning is only revealed when we see it as part of a larger system, with a history of interactions and a future that is still unfolding. This need for contextual analysis is why modern observatories don't just take pretty pictures. They gather data across the entire electromagnetic spectrum. By combining optical images with infrared views that can peer through dust, radio maps that trace cold gas, and X-ray observations that reveal superheated material, we can piece together the full story of a galactic merger and avoid being fooled by its most spectacular deceptions. These illusions, therefore, have not hindered our progress. They have forced us to become better cosmic detectives, teaching us to look beyond the immediate appearance of things and to read the deeper history written in the motions of stars and the glow of scattered gas. Humanity has always looked to the heavens for signs, for patterns that might reveal a hidden order or a divine plan. This deep-seated need to find meaning in the stars brings us to our 29th great cosmic illusion, one that is woven into the very fabric of human psychology, the compelling and often misleading allure of cosmic alignment. Throughout history, the predictable yet awe-inspiring choreography of the heavens has been misinterpreted as a direct message from the gods, a portent of earthly events, or evidence of a grand, intentional design. Even today, in our age of advanced science, we are not immune to this tendency. The random arrangements of natural objects or even our own artificial creations in space can trick our pattern-seeking brains into seeing purpose where there is only chance, reminding us that the most persistent cosmic illusions are often the ones we create ourselves. The historical record is filled with stunning examples of this phenomenon. Ancient civilizations from the Mayans to the Egyptians possessed incredibly sophisticated astronomical knowledge, tracking the cycles of Venus and the phases of the Moon with remarkable precision. Yet, this knowledge was frequently intertwined with a belief that celestial events were omens. A planetary conjunction, where several planets appear to cluster together in the night sky, was rarely seen as a simple consequence of orbital mechanics. Instead, it was interpreted as a harbinger of a king's death, a sign of impending war, or a message of favor from a deity. Eclipses, in particular, were viewed with sheer terror across countless cultures, seen as a dragon or demon devouring the sun, requiring loud noises and rituals to frighten the celestial monster away and restore light to the world. These interpretations were not born out of ignorance, but from a profound and understandable desire to connect the vast, impersonal cosmos to the intimate narrative of human life. The sky was the biggest screen imaginable, and it was only natural to believe that the stories playing out there were somehow about us. In our modern era, we might smile at these ancient beliefs, confident that we have outgrown such superstitions. But the human brain's pattern recognition software is ancient and powerful, and it operates just as strongly today. A fascinating modern example can be found in the orbits of certain asteroids. The vast majority of asteroids follow orbits that are, to our best measurements, random and chaotic, shaped by billions of years of gravitational interactions. However, every now and then, astronomers will identify a small group of asteroids whose orbital paths appear to be strangely similar. The immediate, tantalizing question arises: could these be fragments of a larger parent body that broke apart? This is a perfectly valid scientific hypothesis, but the illusion emerges when we consider the possibility of artificiality. The idea that such a grouping could be anything other than natural requires an enormous leap, yet it is a leap that our pattern-hungry minds are all too willing to make, if only for a thrilling moment. It takes rigorous spectral analysis and detailed orbital projections to confirm a common origin, or, more often, to reveal the alignment as a temporary and coincidental grouping that will be ripped apart by gravity over time. This illusion extends beyond natural objects to things we ourselves have put into space. Consider the growing constellations of satellites, like SpaceX's Starlink network, which are being deployed to provide global internet coverage. When first launched, these satellites travel in a tight train, appearing as a string of pearls moving methodically across the twilight sky. For anyone unfamiliar with this modern project, the sight is utterly bewildering and can easily be misinterpreted as a single, impossibly large structured object or a coordinated fleet of unknown origin. Even the predictable paths of geostationary satellites, which hang fixed in the sky relative to the Earth, can create alignments with stars or planets that look deliberate to the casual observer. These are not omens, of course, but they are a powerful testament to how easily ordered motion can be perceived as intentional design, a ghost of meaning imposed upon the blank canvas of space. The real value of recognizing this cosmic illusion is not to mock our ancestors or ourselves for seeing patterns, but to appreciate the crucial role that science plays in separating compelling coincidence from genuine truth. The scientific method is, in many ways, a disciplined system designed to counteract our innate cognitive biases. It demands evidence, replication, and logical consistency. It takes the breathtaking sight of a planetary alignment and doesn't just leave us in awe. It gives us the physics to calculate exactly when the next one will occur, demystifying the event while simultaneously deepening our appreciation for the real, mechanical beauty of the solar system. Science dispels the myth of the eclipse as a monster by explaining the sublime geometry of orbital shadows, allowing us to predict these events centuries in advance and transforming an experience of fear into one of communal wonder and scientific inquiry. This process doesn't rob the universe of its majesty. It replaces a shallow superstition with a much deeper and more profound understanding. By resisting the easy temptation to see a message in every random alignment, we open ourselves up to discovering the true and often far more astonishing laws that actually govern the cosmos. Perhaps no particle in the universe is as notoriously elusive or as fiendishly difficult to pin down as the neutrino. These ghostly subatomic particles are born in the heart of stars, in the violent aftermath of supernova, and even in the core of our own planet, and they flood through the cosmos in unimaginable numbers. Trillions of them pass through your body every second, interacting with virtually nothing, their presence betrayed only by the most delicate and sophisticated detectors ever built. It is this very ghost-like nature that makes them so fascinating to physicists, as any deviation from their expected behavior could be a crack in the door to an entirely new realm of physics beyond our current standard model. But this same elusiveness also makes them the perfect vehicle for one of the most dramatic and instructive cosmic illusions of the modern era. A stark lesson in how the desperate desire for a breakthrough can be momentarily blinded by a simple, mundane error. The stage for this illusion was set in 2011 by the Opera Experiment, a massive international collaboration buried deep under the Gran Sasso mountain in Italy. Their goal was to fire a beam of neutrinos from CERN over 700 kilometers away in Switzerland and time their journey with exquisite precision. According to Einstein's theory of special relativity, nothing can travel faster than the speed of light in a vacuum, a cosmic speed limit that has withstood every test for over a century. The neutrinos racing through the rock should have arrived just slightly after a beam of light would have made the same trip. The initial results, however, sent a seismic shock through the global physics community. The Opera team's data suggested the neutrinos were arriving 60 nanoseconds earlier than they should have, a tiny fraction of a second, but a colossal discrepancy that implied they were breaking the ultimate cosmic speed limit. The announcement was made with caution, but the implication was electrifying. If true, it would have been the most profound physics discovery in decades, potentially unraveling the very foundation of modern physics. The scientific world erupted. Headlines around the globe screamed that Einstein might have been wrong. Theorists scrambled to produce papers explaining how such faster-than-light travel could be possible within exotic new frameworks. Yet beneath the excitement, a deep and healthy skepticism prevailed. The entire edifice of modern physics, from how stars shine to how magnets work, is built upon the unshakable constancy of the speed of light. To overturn it would require more than a single anomalous result. It would require ironclad, reproducible proof. Other experiments, like MINOS in the United States and T2K in Japan, began analyzing their own data, looking for a similar effect. The Opera team itself invited intense scrutiny, pleading for other groups to help them find what they might have missed. This is the scientific process at its very best. A claim of an extraordinary discovery met not with blind acceptance, but with a collective, rigorous effort to verify or debunk it. The resolution, when it came months later, was as humble as the initial claim was grand. The culprit was not a flaw in relativity, but a flaw in the experimental setup, a heartbreakingly simple one. A bad connection between a fiber optic cable and a computer card was causing a tiny, systematic delay in the GPS timing signal used to synchronize the clocks at CERN and Gran Sasso. Furthermore, an internal oscillator used in the experiment was found to be slightly miscalibrated. These two small, technical errors conspired to make the neutrinos' travel time appear shorter than it actually was. Once these issues were identified and corrected, the 60 nanosecond advantage vanished completely. The neutrinos were, as Einstein had decreed all along, respectably slower than light. The faster-than-light result was a mirage, a phantom signal born from the most mundane of origins, a loose cable. This episode is far from a black mark on science. It is a brilliant testament to its ultimate strength and integrity. It demonstrates the powerful self-correcting mechanism that is built into the scientific method. No single experiment, no matter how prestigious, is ever the final word. Every claim must survive the brutal, unforgiving gauntlet of independent verification. The Opera collaboration, to its immense credit, handled the situation with remarkable transparency and humility, openly inviting criticism and ultimately correcting their own mistake. The mirage of the superluminal neutrino taught the world a vital lesson about the nature of discovery at the very frontier of knowledge. It showed that our most precise measurements are always vulnerable to subtle, almost invisible flaws, and that the path to truth is not a straight line from hypothesis to confirmation, but a winding road filled with dead ends, wrong turns, and necessary corrections. It is a process that demands not just brilliance, but an unwavering commitment to skepticism, especially towards our own most exciting results. At the heart of some of the most profound mysteries in physics lies a seemingly simple question with devastating implications. What happens to the information that falls into a black hole? This puzzle, known as the black hole information paradox, pits two of our most successful theories against each other in a fundamental conflict that has spawned decades of debate and some of the most creatively speculative ideas in modern science, creating a powerful illusion that we are closer to a solution than we truly are. The problem begins with the straightforward principles of quantum mechanics, which dictate that information about the state of a particle, its position, its velocity, its spin, can never be truly destroyed. It might be scrambled and rendered unrecognizable, like burning a book to ashes, but in principle, a hypothetical omnipotent being could reverse the process and reconstruct the book from the smoke and ash. Information in the quantum sense must be conserved. Now enter the black hole as described by Einstein's general relativity. According to the classical view, if you throw that same book into a black hole, it is irretrievably gone. It passes through the event horizon, the point of no return, and is crushed into the infinitely dense singularity at the center. The black hole itself retains only three pieces of information: its mass, its electric charge, and its spin. Everything else about the book, the author, the plot, the specific arrangement of its atoms seems to have been erased from the universe forever. This is a direct violation of quantum law. The plot thickened with Stephen Hawking's groundbreaking work in the 1970s. He showed that black holes are not entirely black. Due to quantum effects near the event horizon, they slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation, however, presents the final nail in the coffin for information. Hawking calculated that this radiation is purely thermal. It is random noise, completely devoid of any information about what fell into the black hole. So, when the black hole finally evaporates completely, all it leaves behind is this featureless thermal radiation. The information about the book appears to have been lost forever, not just hidden behind a horizon, but utterly obliterated. This conclusion was so unsettling that Hawking himself initially declared that it meant quantum mechanics itself must be rewritten, a statement that sent shockwaves through the theoretical physics community. The paradox was born. Quantum mechanics says information cannot be lost, but our best calculations for black holes say that it is. This intellectual crisis has acted like a forge for brilliant, if highly speculative, solutions. The desire to resolve the paradox and save the sanctity of quantum mechanics has led theorists to propose breathtakingly exotic concepts that often feel more like science fiction than science. One of the most prominent is the idea of black hole complementarity, which suggests that from the perspective of an outside observer, information never actually crosses the event horizon but is instead smeared across it, encoded in a scrambled, two-dimensional form. This connects to the fascinating holographic principle, the idea that all the information describing a three-dimensional volume of space can be represented on its two-dimensional boundary. Much like a hologram on a credit card contains all the information for a three-dimensional image. In this view, the black hole's event horizon acts as a vast cosmic hard drive, storing a perfect record of everything that ever fell in. The information isn't lost, it's just stored in a format we don't yet know how to read. An even more radical and disturbing proposal is the firewall hypothesis. This idea suggests that the smooth, empty space predicted by Einstein at the event horizon is an illusion. Instead, there might be a literal wall of incredibly energetic particles, a firewall, that would instantly incinerate anything crossing the horizon. This violent proposal emerges from an attempt to prevent information from being duplicated, which quantum mechanics also forbids. If information is both radiated away by Hawking radiation and remains inside the black hole, you have an illegal copy. A firewall would destroy the incoming object, ensuring its information is only released back into the universe through radiation, preventing any duplication. The problem, of course, is that this completely contradicts general relativity, which guarantees that an astronaut crossing the event horizon should feel nothing unusual at all until they are eventually spaghettified by tidal forces much later. So we are left choosing which fundamental law to break, quantum mechanics or relativity. The great illusion of the information paradox is not that these ideas are without merit. They are ingenious and have profoundly advanced our conceptual understanding. The illusion is the sense that one of these compelling narratives must be correct and that we are on the verge of a solution. The reality is that these ideas remain almost entirely in the realm of mathematical speculation. They are stories we tell to make the equations consistent, but they are not yet science in the empirical sense. They make no testable predictions that we can currently verify with observation or experiment. We cannot probe the event horizon of a black hole to see if it's a smooth spacetime continuum, a shimmering hologram, or a raging firewall. These concepts race far ahead of our ability to test them, creating a persuasive illusion of progress that is built on mathematical elegance and internal consistency rather than empirical evidence. The ghost of the information paradox continues to haunt physics, not because we lack creativity, but because the universe guards its deepest secrets behind an horizon that may be fundamentally impenetrable, reminding us that some of the most beautiful ideas in science can remain tantalizingly out of reach, compelling phantoms in the vast darkness of our ignorance. Imagine a universe where the familiar three dimensions of space and one of time are not the whole story, but merely the visible tip of a vast, hidden multidimensional reality. This is not science fiction, but a serious proposal from some of the most advanced theories in physics, most notably string theory. The mathematics behind these ideas is often breathtakingly beautiful, suggesting a cosmos woven from tiny, vibrating strings whose harmonies require 6 or 7 additional spatial dimensions to be mathematically consistent. These extra dimensions, the theory suggests, are curled up into shapes so infinitesimally small that we cannot perceive them directly, yet their existence could elegantly explain some of the most perplexing mysteries in physics. For instance, the inexplicable weakness of gravity compared to the other fundamental forces might be because gravity, unlike electromagnetism, is not confined to our three-dimensional brain of existence, but is instead free to leak away into these other dimensions, diluting its strength. In an even more tantalizing twist, what we perceive as the mysterious, invisible mass of dark matter might not be a new particle at all, but merely the gravitational shadow of ordinary matter residing in a parallel three-dimensional universe separated from us by a minuscule gap in a higher dimension. The sheer intellectual appeal of these ideas is undeniable. They offer a powerful narrative of unification and hidden simplicity, promising to tie up the messy loose ends of the cosmos with a single, elegant mathematical bow. This compelling allure, however, has also given rise to a profound and subtle cosmic illusion, the conflation of mathematical necessity with physical truth. The human mind, especially the mind of a theoretical physicist, is powerfully drawn to elegance and beauty. When a set of equations possesses a deep internal consistency and symmetry, it creates a strong psychological pull to believe that it must describe reality. String theory and its multidimensional cousins are masterpieces of mathematical architecture, and this very brilliance has tricked many into a sense of their inevitability. For decades, the search for evidence of extra dimensions has been a holy grail, with experiments designed to detect their subtle signatures. Particle colliders like the Large Hadron Collider have searched for missing energy that could be carried away by particles darting into other dimensions. Precision measurements of the force of gravity at sub-millimeter scales have looked for deviations from Newton's inverse square law, which would occur if gravity were taking a shortcut through an extra dimension. Yet, despite this immense effort, the results have been a resounding silence. No missing energy, no deviations from the expected gravitational force, no shred of empirical evidence has been found to confirm that these beautiful mathematical constructs are anything more than intricate and sophisticated illusions. This ongoing search forces a crucial and often humbling distinction between a mathematically possible universe and the one we physically inhabit. The history of science is littered with beautiful theories that were ultimately discarded because they did not align with observation. The geocentric model of the cosmos, with its complex system of planetary epicycles, was a mathematically elegant way to save the appearances of the celestial motions, but it was ultimately a fiction, replaced by the simpler heliocentric reality. The lesson here is that mathematical beauty is a fantastic guide for generating hypotheses, but it is not a substitute for experimental verification. Cosmology and fundamental physics are not branches of pure mathematics. They are empirical sciences. Their ultimate authority does not come from the elegance of their equations on a blackboard, but from their ability to predict and explain the data we collect from telescopes, particle detectors, and other instruments. The deceptive simplicity offered by extra dimensions serves as a powerful reminder that the universe is under no obligation to conform to our aesthetic preferences for neat and tidy solutions. It may be that the truth behind dark matter and the hierarchy of forces is far messier, far more complex, or simply something we haven't even begun to conceive of yet. The greatest challenge and the true path to discovery lies in maintaining a delicate balance, to be inspired by the beauty of the mathematics, but to never be fooled by it, always demanding that the cosmos itself has the final say. Imagine a universe that is not a single, finished product, but an endlessly blooming flower, perpetually giving birth to new realities in a frenzy of exponential expansion that never, ever stops. This is the breathtaking, and some might say bewildering, concept of eternal inflation. It takes the already radical idea of cosmic inflation, that brief, faster-than-light growth spurt in our universe's infancy, and extrapolates it to its ultimate conclusion. According to this theory, the inflating spacetime that spawned our cosmos isn't a one-time event. It's a permanent, fundamental state of existence. In this picture, what we call the Big Bang was merely the moment our local region of this eternally inflating meta-universe happened to slow its expansion and crystallize into the stable, star-filled cosmos we recognize. But elsewhere, the inflationary process continues unabated, and in those regions, new bubble universes are constantly nucleating, each with its own potentially unique set of physical laws and constants. Our entire observable universe, with its hundreds of billions of galaxies, becomes just one bubble in an infinite, frothing cosmic foam, a single page in an endless library of realities known as the multiverse. The theoretical elegance of this idea is immense. It offers a tantalizing potential explanation for one of the most stubborn puzzles in all of physics. Why do the fundamental constants of our universe seem so exquisitely fine-tuned for the existence of life? If there are an infinite number of universes, each with randomly different laws, then it's no surprise we find ourselves in one of the rare habitable ones. The multiverse theory doesn't require a creator or a deeper reason for the fine-tuning. It simply invokes the sheer, mind-numbing power of infinite probability. This makes it an incredibly seductive solution for many cosmologists. However, this very seduction gives rise to one of the most profound philosophical illusions in modern science, the illusion of explanatory power. Eternal inflation appears to explain everything, but in doing so, it risks explaining nothing at all. If a theory can be invoked to account for any possible set of observations, then it becomes fundamentally unfalsifiable. How could we ever prove the existence of these other universes if they are, by their very definition, forever beyond our causal horizon, separated from us by regions of space that are still inflating faster than light can travel? This challenge of testability has not stopped physicists from trying. The most promising avenue has been to look for potential scars or echoes of our universe's violent birth within the multiverse. If our bubble universe collided with another one in the distant past, the energy released in that cosmic fender bender could have left a specific circular imprint on the oldest light we can see, the cosmic microwave background. For a time, there was tremendous excitement around certain anomalous features in the CMB maps, like the famous cold spot, which some researchers suggested could be the bruise from such a collision. It was a thrilling possibility, the first empirical evidence for a reality beyond our own. But as with so many cosmic illusions, closer inspection with more powerful telescopes, like the Planck satellite, revealed a more mundane truth. The anomalies were far more likely explained by a combination of statistical flukes. The universe is bound to have some rare cold patches purely by chance, and unsubtracted foreground emission from dust within our own galaxy. The signature of the multiverse, it seemed, had dissolved into noise. This cycle of exciting proposal and subsequent debunking highlights the immense difficulty of doing science on the multiverse scale. It forces a critical and often uncomfortable dialogue between two essential pillars of scientific progress: unbridled creativity and rigorous empirical discipline. On one hand, ideas like eternal inflation are vital. They push the boundaries of our imagination, forcing us to consider possibilities far beyond our everyday experience and challenging us to develop new mathematics and new conceptual frameworks. They are the engines of theoretical innovation. On the other hand, science cannot survive on creativity alone. For an idea to graduate from captivating speculation to accepted theory, it must make specific, testable predictions that can be verified or refuted through observation and experiment. The history of physics is littered with beautiful ideas that were ultimately discarded because they failed this crucial test. The current struggle with eternal inflation is a live action demonstration of this tension. It urges a delicate balance, a reminder that while we should dare to dream of infinite universes, we must also keep our feet firmly planted in the data from this one, ensuring that our most ambitious theories remain connected to the reality we can actually observe and measure. The concept of a universe with a definitive beginning and a potentially lonely end can feel strangely limiting, almost claustrophobic in its linearity. What if, instead of a single, one-way journey from a big bang to a cold, dark fade, the cosmos is engaged in an eternal, rhythmic dance of death and rebirth? This is the captivating premise of cyclic universe models, an idea as ancient as Hindu cosmology and as modern as cutting-edge theoretical physics. These models propose that our universe is not the first and only chapter, but merely the current iteration in an endless cycle. Each eon begins with a big bang, expands for billions of years, and then, rather than fading into nothingness, reverses course in a big crunch, collapsing back into an ultra-dense state that then triggers the next big bang, resetting the cosmic clock for another turn. This vision of an eternally recurring cosmos is profoundly seductive, offering a kind of philosophical comfort and an elegant closure that the standard, lonely expansion model lacks. It suggests a universe that is immortal and self-renewing, and for decades, proponents have searched for its ghostly signature in the deepest data we can collect, sometimes believing they've found convincing evidence. only to discover the universe is once again practicing its masterful art of deception. The hunt for evidence of a cyclic past is a search for cosmic fossils, for echoes of a previous eon that might have imprinted themselves onto the very fabric of our own. The most promising place to look is once again the cosmic microwave background, that fossilized light from our own universe's infancy. The theory suggests that if our cosmos was indeed born from the collapse of a previous one, the gravitational waves generated in the violent death throes of that prior universe could have left a specific, faint pattern in the polarization of the CMB. This signature would be the ultimate smoking gun, a direct message from a universe that existed before time as we know it began. Similarly, certain subtle anomalies in the temperature fluctuations of the CMB, patterns that don't quite fit the predictions of the standard inflationary model, have been put forward as potential evidence of a pre-Big Bang phase. The allure of these ideas is powerful. They promise to connect our reality to a grander, infinite narrative, making our existence part of an eternal story rather than a solitary, fleeting event. Yet, this grand and beautiful narrative constantly runs aground on the hard rocks of empirical evidence and alternative explanations. The supposed signatures of a cyclic universe, much like the evidence proposed for cosmic strings or the multiverse, are frustratingly non-unique. The specific patterns in the CMB that one theorist might attribute to a previous cosmic cycle can be, and often are, just as easily explained by more conventional physics within the standard single-universe model. For instance, the gravitational wave signal that would be a hallmark of a cyclic model is virtually indistinguishable from the signal predicted by certain versions of inflationary theory. When the BICEP2 team announced their detection of B-mode polarization, it was a moment of excitement not just for inflation proponents but also for some cyclic model advocates who saw it as potential evidence for their own theory. The subsequent realization that the signal was galactic dust was a disappointment to all, but it perfectly illustrated the problem. The data was ambiguous, open to multiple, wildly different interpretations. This ambiguity is the core of the illusion. The human mind, when presented with a compelling story and a faint, unclear signal, is incredibly adept at connecting the dots, even if those dots are just random noise arranged in a suggestive pattern. This ongoing challenge highlights the critical and often painfully slow dialogue between mathematical elegance and physical proof in cosmology. Cyclic models are intellectually beautiful and philosophically satisfying. They resolve the thorny question of an absolute beginning and offer a neat, packaged vision of eternity. But a compelling narrative is not enough. For a theory to move from the realm of captivating speculation to established science, it must make a clear, testable prediction that is unique to it, a prediction that cannot be explained by any other model. So far, the cyclic universe has struggled to provide such an unambiguous prediction. Its proposed signals consistently overlap with those from other theories, making it impossible to definitively say, this and only this proves the cycle. This doesn't mean the idea is wrong. It simply means it remains, for now, in the category of a brilliant but unverified hypothesis. The mirage of cosmic cycles teaches a vital lesson about the nature of scientific progress. It shows us that the most seductive theories are often the ones we must scrutinize the most fiercely, demanding from them not just beauty and grandeur, but clear, unequivocal evidence that can stand up to the relentless, skeptical gaze of the entire cosmos. Science fiction has a remarkable power to shape our scientific ambitions, planting seeds of incredible ideas that blur the line between fantasy and future possibility. Among the most captivating of these concepts is the wormhole, a cosmic shortcut, a tunnel through the folded fabric of spacetime that could connect two impossibly distant points in the universe, or perhaps even bridge different universes altogether. This stunning idea didn't originate in a physics lab. It emerged from the minds of theorists like Albert Einstein and Nathan Rosen, who found that their equations for general relativity allowed for such structures, which they called Einstein-Rosen bridges. But it was the world of storytelling that truly launched them into our collective imagination, presenting them as the ultimate tool for interstellar travel and a gateway to wonders beyond our comprehension. This blend of theoretical possibility and narrative allure has driven a very real, decades-long scientific quest to find evidence that these space-time tunnels are more than just mathematical curiosities, that they might actually be out there, hidden in the depths of the cosmos. The search, however, has been a masterclass in cosmic deception, a journey filled with tantalizing false leads that reveal just how cleverly the universe can mimic our wildest dreams with utterly ordinary phenomena. The primary strategy for hunting these phantom structures relies on their most dramatic predicted effect, extreme gravitational lensing. We know that any massive object, like a galaxy or a black hole, can bend the light from objects behind it, acting as a cosmic magnifying glass. But a wormhole, with its unique topology, a throat connecting two mouths, would theoretically create a lensing signature unlike any other. Instead of producing the familiar arcs or multiple images we see from galaxies, a wormhole might create a strange, telltale pattern of rings or a peculiar duplication of a single object with specific, identifiable distortions. Astronomers have scoured the sky for these anomalous patterns, and on several occasions they've believed they had a candidate. A curious set of twin quasars or a strangely symmetrical arrangement of light around a distant galaxy cluster can send a jolt of excitement through the astrophysics community. The immediate, thrilling question arises, could this be it? Could we be looking at the mouth of a tunnel through space-time? Time and again, the answer has been a sobering no. Those tantalizing twin images almost always turn out to be the perfectly mundane result of two separate galaxies, aligned almost perfectly along our line of sight, a simple trick of perspective. The strange rings or distortions are later revealed to be caused by the complex interplay of gravity within a massive cluster of galaxies, or even by subtle errors in the image processing software used to sharpen the incredibly faint signals from the edge of the observable universe. The universe, it seems, has a limited repertoire of special effects, and it often reuses them. What looks like the signature of a space-time warping tunnel is usually just a more common cosmic structure viewed from a fortunate or unfortunate angle. These repeated false positives are not failures. They are an essential part of the scientific process, forcing researchers to develop ever more sophisticated algorithms and statistical methods to rule out the mundane before leaping to the extraordinary. Each illusion makes our cosmic census that much more accurate, even if it doesn't deliver the revolutionary discovery we hoped for. This ongoing hunt illustrates a profound and beautiful aspect of how science actually works. The line between inspiration and implementation is not a barrier but a bridge. The fantastical idea of a wormhole, born from mathematics and popularized by fiction, provides a compelling target, a concrete question to ask of the data. What would this look like if it were real? This motivates the development of new technologies and new analytical techniques. The desire to find a wormhole pushes us to build better telescopes and write more complex data analysis code, tools that then benefit all of astronomy, even if their original target remains elusive. The rigorous standards required to avoid false leads, the demand for multiple lines of evidence, the insistence on peer review, the healthy skepticism that greets every extraordinary claim ensure that the process remains honest. They prevent us from falling in love with a beautiful illusion and ensure that if a wormhole is ever truly found, the evidence will be so overwhelming and bulletproof that it will forever change our understanding of the universe. The phantom signals from wormholes teach us that the path to discovery is not a straight line from fiction to fact, but a winding road where our greatest inspirations are rigorously tested against the uncompromising reality of the cosmos. For all its apparent consistency as a steady beacon in our sky, our sun is a seething, chaotic ball of plasma whose inner workings are far more complex and unpredictable than we often care to admit. This brings us to our 36th great cosmic illusion, the deceptive regularity of solar activity. For centuries, astronomers have tracked the sunspot cycle, noting that the number of dark blemishes on the sun's surface rises and falls with a rough period of about 11 years. This observation created a powerful expectation of order, a comforting rhythm that suggested we could forecast the sun's tantrums, much like we predict the changing seasons on Earth. We built intricate models based on this perceived periodicity, attempting to predict the strength and timing of future solar cycles with the hope of anticipating the solar storms that can wreak havoc on our technology-dependent civilization. Yet, time and again, the sun defies these predictions with a randomness that reveals our models to be little more than educated guesses, humbling reminders that we are observing a dynamic system whose core engine remains one of the great unsolved mysteries of astrophysics. The consequences of this illusion are not merely academic, they are profoundly practical and economic. Our modern world is incredibly vulnerable to the sun's outbursts, a phenomenon collectively known as space weather. A powerful coronal mass ejection, a billion-ton cloud of magnetized plasma hurled from the sun, that travels directly toward Earth can induce massive electrical currents in our planet's crust. These geomagnetic storms have the potential to cripple national power grids, causing widespread blackouts that could last for months. They can fry the sensitive electronics aboard satellites, wiping out global positioning systems, telecommunications, and weather forecasting capabilities in an instant. They also pose a significant radiation hazard to astronauts in orbit and to pilots and passengers on high-altitude polar flights. The ability to accurately predict such an event, to give power grid operators and satellite controllers even a few days warning to take protective measures, is a multi-billion-dollar imperative. This high stakes need fuels a relentless drive to find patterns and create reliable forecasts, a drive that is constantly frustrated by the sun's inherent capriciousness. The root of this deception lies in the solar dynamo, the natural generator deep within the sun that produces its magnetic field. This process is a form of magnetohydrodynamics, a fiendishly complex interplay between the sun's intensely hot plasma, its rotation, and its own internal convection currents. While the 11-year cycle is a real phenomenon, it is merely an average, a blurry statistical snapshot of a process that is fundamentally chaotic. Some cycles are incredibly intense, with sunspot numbers soaring. Others are remarkably weak and prolonged. The famous Maunder minimum in the 17th century, for instance, was a period of 70 years when sunspots virtually vanished, coinciding with the coldest part of the Little Ice Age on Earth. Our current predictive models, which often rely on tracking the behavior of magnetic fields at the sun's poles at the end of one cycle to forecast the strength of the next, have a spotty record at best. They completely failed to predict the peculiar weakness of solar cycle 24, which peaked in 2014, leaving solar physicists scrambling for explanations. It appears that the solar dynamo operates on multiple overlapping cycles and is influenced by deeper, slower currents that we cannot yet observe, making its output as predictable as the path of a single molecule in a hurricane. This recurring failure is a masterclass in the challenges of forecasting any complex, non-linear system, whether it's the sun, Earth's climate, or the global economy. We are wired to seek patterns, to extrapolate curves, and to believe that the recent past is a reliable guide to the near future. The Sun constantly reminds us that this is a dangerous assumption. Its unpredictable nature forces a necessary humility upon the sciences of heliophysics and climatology alike. It teaches us that we must build technological systems robust enough to withstand surprises from space, and that our models must always be viewed as imperfect approximations of a reality far more complicated than we can currently grasp. The illusion of solar predictability is not a failure of science, but a call to deepen it, to peer more intently into the heart of our star with newer tools and more sophisticated theories, accepting that true understanding may require us to embrace the beautiful, chaotic truth rather than the comforting, orderly illusion. We build our entire understanding of the cosmos upon a foundation of unwavering trust, a belief that the fundamental rules of the game have not changed since the very first moment of the Big Bang. This principle, known as the constancy of physical constants, is the bedrock of cosmology. It allows us to look at the light from a galaxy 10 billion light-years away and be confident that the atoms within it were governed by the same physics, the same strength of forces, and the same speed of light as the atoms in our bodies here on Earth today. It is this assumed stability that lets us use the distant universe as a laboratory, comparing then and now to understand how cosmic evolution truly works. But what if this foundational trust is misplaced? What if the rules themselves are slowly, subtly changing over the immense span of cosmic time? This terrifying and thrilling possibility has occasionally seemed to reveal itself in the data, creating one of the most profound and far-reaching cosmic illusions, one that strikes at the very heart of our scientific method. The most famous and persistent of these challenges has centered on a crucial number known as the fine structure constant, often denoted by the Greek letter alpha. This isn't a constant you learn about in high school, but it is arguably one of the most important numbers in all of physics. It is a pure, dimensionless value that defines the strength of the electromagnetic force, governing how tightly electrons are bound to an atom's nucleus and how light and matter interact. Its value, approximately 1/137th, is what makes chemistry possible and dictates the very structure of reality as we know it. For decades, a team of astronomers has used the world's most powerful telescopes to meticulously study the light from incredibly distant quasars. As this light travels for billions of years to reach us, it passes through clouds of interstellar gas. Atoms within these clouds absorb specific wavelengths of the quasar's light, leaving behind a unique barcode of dark lines in the spectrum. The precise position of these absorption lines is exquisitely sensitive to the value of the fine structure constant. The team's astonishing claim was that in certain directions of the sky, the patterns of these lines were subtly shifted in a way that suggested alpha was slightly smaller billions of years ago than it is today. The implication was earth-shattering. The laws of physics were not immutable, but were themselves evolving alongside the universe. The scientific community was electrified and deeply skeptical in equal measure. A varying constant would force a rewrite of virtually all of modern physics, from quantum electrodynamics to general relativity. It would mean that the universe of the past was fundamentally different from the universe of the present, and that our confident extrapolations back to the first second of the Big Bang were built on sand. The hunt for errors began, and it is in this rigorous, painstaking process that we find the true lesson of this cosmic illusion. Other research groups, using different telescopes and different analytical methods, struggled to reproduce the result. The culprit, it turned out, was not in the stars, but in the incredibly complex and subtle instruments we use to observe them. The high-resolution spectrographs used for these measurements are miracles of engineering, but they are not perfect. Minute temperature changes in the observatory dome can cause the metal components of the spectrograph to expand or contract by microscopic amounts, enough to slightly shift the calibration of the entire instrument. Even more insidiously, the models used to subtract the background noise and the Earth's own atmospheric interference from the signal can inadvertently introduce tiny, systematic biases that masquerade as a physical effect. What looked like a change in a fundamental constant of nature was, in all likelihood, a fantastically convincing phantom born from a combination of unaccounted for instrumental drift and the statistical magnification of tiny, random uncertainties across vast cosmic distances. This episode is far from a scientific failure. It is a stunning triumph of the self-correcting mechanism that is the very soul of the scientific process. It reinforces a humbling and vital truth. The more extraordinary the claim, the more ordinary the explanation is likely to be. The illusion of varying constants forced a monumental improvement in our methodological rigor. It drove engineers to build more stable, temperature-controlled spectrographs and prompted data analysts to develop more robust statistical techniques to guard against their own unconscious biases. It serves as a permanent cautionary tale that our thirst for revolutionary discovery must always be tempered by a profound respect for the limitations of our tools and our own fallibility. The constancy of the laws of physics remains our best, most tested assumption, not because we are closed-minded, but because every time a challenge has arisen, it has been met with a level of scrutiny that only reinforces the resilience of the foundation. The universe may be full of illusions, but the slow, careful, and collaborative work of science remains our most powerful tool for seeing through them, ensuring that when a real revolution does come, we will be able to recognize it for what it is. Just as we grapple with mysteries within our observable cosmic horizon, an even more tantalizing puzzle emerged from the careful study of how the largest structures in the universe appear to move. This brings us to the mirage of dark flow, a phenomenon that for a brief, thrilling moment seemed to point to something vast and unknown exerting its influence from beyond the edge of everything we can see. The story begins with the fundamental expectations set by the Big Bang Theory and the concept of cosmic inflation. On the very largest scales, the universe should be expanding in a homogeneous and isotropic way, meaning that the motion of galaxy clusters should be random and evenly distributed in all directions, like dots on an inflating balloon that all move apart from one another without any preferred direction. This uniform expansion, driven by the overall stretching of space, is the default assumption, the cosmic null hypothesis. However, when a team of astronomers led by Alexander Kashlinsky analyzed data from the Wilkinson microwave anisotropy probe, they found something that seemed to violate this foundational principle. By studying the subtle motions of massive galaxy clusters, they detected a curious and unexpected signal. It appeared that a large number of these clusters were not just moving with the general expansion of the universe, they were also all streaming in the same specific direction at astonishing speeds of nearly 1,000 kilometers per second. This coordinated motion was dubbed the dark flow, a name chosen to echo other cosmic mysteries like dark matter and dark energy, suggesting a hidden, unknown cause. The most radical and breathtaking interpretation was that this flow was being caused by the gravitational pull of something immense that lay far beyond our observable universe. The observable universe is a bubble defined by the distance light has had time to travel since the Big Bang, but inflation theory suggests the entire cosmos is vastly larger. The dark flow, if real, would be our first ever empirical hint of what lies in that unobservable beyond. Perhaps a massive concentration of matter left over from the pre-inflationary era, a cosmic structure so enormous it could tug on entire galaxy clusters from the other side of reality. This proposition sent shockwaves through the cosmology community. The idea that we could somehow detect the influence of a region of space we can never directly observe was both revolutionary and deeply unsettling. It promised a crack in the door, a way to peer beyond the ultimate horizon. But in science, extraordinary claims inevitably face an onslaught of scrutiny, and the dark flow hypothesis was no exception. Other teams of researchers set out to verify the result using different methods and newer data from the more advanced Planck satellite. As they peeled back the layers of this complex measurement, the initial, thrilling signal began to crumble. The primary culprit was identified as a systematic error, a subtle but critical artifact in how the data was processed. The specific technique used involved comparing the cosmic microwave background, the ancient light from the early universe, with the distribution of nearby galaxy clusters. It was a fiendishly difficult measurement, requiring astronomers to subtract our own solar system's motion through the cosmos, account for the local gravitational pull of the Milky Way and its neighbors, and isolate a truly peculiar velocity from the dominant Hubble flow of expansion. It turned out that incomplete subtraction of these local foreground effects had created a phantom signal, a coordinated motion that wasn't really there on a cosmological scale. What looked like a mysterious flow from beyond was, in reality, a reflection of our own local cosmic neighborhood's gravitational dynamics and the limitations of our measurement techniques. The story of the dark flow is a powerful lesson in the immense challenges of measuring motion on the grandest of scales. It underscores how easily local phenomena can masquerade as global mysteries. This particular illusion, however, was far from a failure. It served as a crucial catalyst for the entire field, driving a significant refinement in the way we measure and interpret cosmic velocities. The debate forced cosmologists to develop more robust statistical methods and more sophisticated models to account for every possible local gravitational influence, from the Great Attractor to the Shapley supercluster. It highlighted the absolute necessity of cross-verification from multiple, independent datasets. The pursuit of the dark flow, even as an illusion, ultimately made our maps of large-scale motions more accurate and our understanding of our local cosmic environment more complete. It stands as a testament to the self-correcting nature of science, where the pursuit of a phantom can lead to very real and valuable progress, ensuring that our next great discovery will be built on a foundation of ever-deepening rigor and humility. Sometimes the most profound cosmic mysteries aren't found in the distant reaches of space, but in the unexpected behavior of our own robotic explorers, sending back data that defies everything we think we understand about physics. This brings us to the fascinating case of the Pioneer Anomaly, a decades-long puzzle that began with two humble spacecraft and nearly upended our understanding of gravity itself. The Pioneer 10 and 11 probes, launched in the early 1970s to explore the outer solar system, were engineering marvels of their time. After completing their primary missions to Jupiter and Saturn, they continued on trajectories that would eventually carry them out of the solar system entirely, becoming silent ambassadors to the stars. As they traveled ever farther from the Sun, teams at NASA carefully tracked their positions using the Deep Space Network, measuring their velocity with incredible precision by analyzing the Doppler shift in their radio signals. Year after year, the data streamed back, and year after year, a tiny, persistent discrepancy began to emerge, one that would captivate and confound physicists for nearly 30 years. Both spacecraft were experiencing a minute, unexplained deceleration. It was an incredibly small effect, roughly 10 billion times weaker than the gravity we feel at Earth's surface, equivalent to the force a single sheet of paper would exert on your hand. But in the precise world of orbital mechanics, where calculations are measured in millimeters per second, this minuscule drag was as glaring as a warning light on a dashboard. The probes were slowing down just slightly more than they should have been. According to Newton's laws of motion and Einstein's general relativity, the only significant force acting on the probes so far from the Sun should have been gravity itself, pulling them backward with a precisely calculable strength. Yet something unknown was tugging on them, creating an anomalous acceleration directed back toward the Sun. This tiny signal refused to go away, and as other potential explanations were ruled out one by one, solar radiation pressure, the gravity of unknown planets, even the influence of dark matter, the mystery only deepened, suggesting the unthinkable, that our fundamental model of gravity might be incomplete or require modification at very large scales. The Pioneer anomaly quickly became a celebrated puzzle in theoretical physics. For scientists, an anomaly that refuses to be explained is the most exciting thing possible, a potential crack in the foundation of known physics where new discoveries can shine through. Dozens of papers were published proposing radical solutions. Perhaps gravity itself didn't strictly follow the inverse square law over extremely large distances, deviating from Newton's predictions in a way we'd never before been able to measure. Maybe it was evidence of a new physical interaction or a subtle effect of the universe's expansion acting on local systems. The anomaly was so clean and persistent that it seemed like the perfect candidate for a revolutionary discovery, a small but real clue that our understanding of the cosmos was about to take a dramatic leap forward. For years, it stood as a challenge to physicists and a testament to the idea that sometimes the biggest secrets are hidden in the smallest of signals. The resolution to this decades-long mystery, however, did not come from a breakthrough in fundamental physics, but from a triumph of painstaking, meticulous engineering detective work. The key was to shift the question from "what new force is doing this?" to "what did we forget about the spacecraft themselves?" A team led by Slava Turyshev at NASA, a jet propulsion laboratory, made a monumental effort to recover and analyze decades-old data, including telemetry records and even original design blueprints that had been stored away for years. They built sophisticated thermal models of the Pioneer probes, simulating every component, every watt of power generated by their radioactive thermoelectric generators, and every possible path that heat could take as it radiated away into the cold of space. Their painstaking work revealed the true culprit, heat, not from the Sun, but from the spacecraft's own onboard systems and electronics. The Pioneer probes were designed with a particular geometry. Their main communication dish acted like a powerful parabolic reflector, but it wasn't just reflecting radio signals, it was also reflecting infrared photons. The heat generated by the spacecraft systems when radiated from the back of the dish would bounce off the dish's support structure and be emitted in a direction that was not perfectly symmetrical. A very slight asymmetry meant that just a few more infrared photons were being emitted in the direction opposite to the spacecraft's motion. According to the simple law of conservation of momentum, each photon carrying energy away from the spacecraft imparts a tiny, minuscule recoil force. When the team calculated the collective effect of billions upon billions of these photons being emitted over decades with this slight directional bias, the numbers aligned perfectly. The mysterious anomalous acceleration was exactly accounted for by the gentle, continuous push of thermal radiation pressure, a force so subtle that it had been overlooked in the original mission planning, but over the vastness of space and time had accumulated into a detectable signal. The story of the Pioneer anomaly is one of the most humbling and instructive in all of modern science. It highlights a crucial truth about exploration. The greatest obstacles to discovery are often not the gaps in our theories, but the hidden assumptions and overlooked details in our own designs. This phantom force, which for years masqueraded as a gateway to new physics, was in fact a masterpiece of cosmic irony, a reminder that every measurement is made through an instrument, and every instrument has its own quirks and personalities. The meticulous investigation that finally solved the mystery did more than just close a chapter. It provided a powerful lesson in the absolute necessity of questioning everything, especially when the answer seems too perfect and too revolutionary to be anything but truth. It stands as a permanent testament to the fact that before we rewrite the laws of the universe, we must first ensure we haven't simply misread the instructions on our own tools. Of all the dreams that drive our exploration of the cosmos, few are more powerful than the search for another Earth, a world orbiting a distant sun, bathed in just the right amount of light to allow liquid water and perhaps even life to exist on its surface. This concept is enshrined in the idea of the habitable zone, a beautiful and intuitive term that has captured the public imagination and become the holy grail of exoplanet science. It's often called the Goldilocks zone, not too hot, not too cold, but just right. When astronomers announce the discovery of a new planet within this sweet spot around its star, headlines understandably erupt with excitement, heralding a potential second home or a bearer of alien biology. This hopeful framing, however, conceals one of the most pervasive and potentially disappointing cosmic illusions: the belief that orbital distance alone can tell us if a world is truly habitable. The reality is that the habitable zone is not a guarantee of life or even of comfort. It is merely the opening bid in a vastly more complex auction where a planet's atmosphere, geology, and even the temperament of its star hold the winning cards. To understand the depth of this deception, we need look no further than our own solar system, which provides a perfect and perfectly terrifying case study. Venus and Earth are often called siblings. They are remarkably similar in size, mass, and rocky composition. Both also orbit squarely within the Sun's habitable zone. By the simple metric of distance, Venus should be a lush, tropical paradise. Instead, it is a blistering hellscape with a surface temperature of 460 degrees Celsius, hot enough to melt lead, crushed under an atmosphere 90 times thicker than Earth's and composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting overhead. Venus is the ultimate cautionary tale, a world that definitively proves that being in the right place is nowhere near enough. Its fate was sealed by a runaway greenhouse effect, a catastrophic positive feedback loop where initial warming led to more water vapor entering the atmosphere, which trapped more heat, which baked more carbon dioxide out of the rocks, which trapped even more heat, until the entire planet was pressure cooked into oblivion. The mere presence of water, or the potential for it, means nothing if a planet's atmospheric chemistry is primed for self-destruction. The lesson of Venus forces us to expand our definition of habitability far beyond a simple orbital diagram. A planet's atmosphere acts as its thermostat, its shield, and its chemical factory all at once. An oxygen-rich atmosphere like Earth's might be a powerful biosignature, but it could also be generated abiotically through the photodissociation of water vapor by ultraviolet light. Conversely, a thick, hazy atmosphere like Saturn's moon Titan could potentially harbor life in its methane seas, even though its surface is far too cold for liquid water. The composition, pressure, and stability of an atmosphere are therefore critical unknowns that can completely override a planet's position in the habitable zone. Just as important is the world beneath our feet, or more accurately, beneath the atmosphere. A planet's geology is its life support system. Earth's long-term climate stability is largely thanks to the carbonate-silicate cycle, a planetary-scale thermostat driven by plate tectonics. This process slowly pulls carbon dioxide out of the atmosphere and locks it away in rocks, preventing a runaway greenhouse effect, and then releases it back through volcanic activity, preventing a global deep freeze. A geologically dead planet without this recycling mechanism could easily seesaw between extreme ice ages and infernos, even if it orbits in the perfect spot. Perhaps the most overlooked variable in the habitability equation is the star itself. We have a deeply ingrained bias toward sun-like stars, but the vast majority of stars in our galaxy are red dwarfs, smaller, cooler, and infinitely more tempestuous than our Sun. Because a red dwarf is so dim, its habitable zone is located incredibly close in, placing any orbiting planet in a gravitational death grip. This proximity often leads to tidal locking, where one side of the planet permanently faces the star in scorching daylight and the other is trapped in eternal, frigid night. This configuration could create a narrow band of potentially temperate twilight at the terminator line, but it presents immense challenges for maintaining a stable atmosphere and distributing heat. Even more dangerous is the stellar activity of these small stars. Red dwarfs are notorious for frequent and violent flares, eruptions that can blast out X-rays and ultraviolet radiation at levels hundreds of times more intense than anything the Sun produces. A planet in the habitable zone of a red dwarf would be subjected to a constant barrage of these sterilizing outbursts, which could strip away its atmosphere and bathe its surface in DNA-shredding radiation, turning a theoretical oasis into a irradiated wasteland. The habitable zone around such a star might be a zone in name only, a mathematical abstraction that bears no relation to the true hostile reality. This complex interplay of factors means that the exciting announcement of a new, Earth-like planet in a habitable zone is more often than not a statement of profound ignorance rather than knowledge. With our current technology, we can often determine a planet's orbital distance and its rough size or mass, but we typically know nothing about its atmosphere, its geology, or the true nature of its star's activity. We are, in effect, seeing a silhouette and declaring we've found a twin. This illusion of habitability is not a failure of science, but a necessary and humbling stage in our learning process. It cautions against the premature excitement that can arise from a single, simple metric and advocates passionately for a more comprehensive, nuanced approach to planetary science. The next generation of telescopes, like the James Webb Space Telescope and future giant observatories on the drawing board, aim to pierce this veil of ignorance. They will be able to analyze the starlight filtering through the atmospheres of these distant worlds, searching for the chemical fingerprints of water vapor, oxygen, methane, and other potential signs of a living, breathing biosphere. The true search for life beyond Earth is only just beginning, and it starts with recognizing that the habitable zone is not a destination, but a starting point, a map that shows us where to look, but one that is still missing almost all of its most important details. For centuries, the astronomer's greatest tool was the human eye, a remarkable instrument but one hopelessly susceptible to deception, fatigue, and the inherent biases of its owner. We gazed at the heavens and interpreted what we saw through the filter of our own expectations, often mistaking atmospheric twinkling for stellar activity or seeing canals on Mars where none existed. Today, we are witnessing a profound revolution, not just in what we can see, but in how we see. The fight against cosmic illusions is no longer waged by lone observers at eyepieces, but by a powerful alliance of cutting-edge hardware and sophisticated software, a technological leap that is finally allowing us to peer behind the universe's grandest magic tricks. This new era is defined by two monumental advancements: unimaginably powerful new telescopes that collect pristine data from the edge of time, and artificial intelligence algorithms capable of sifting through that data with a speed and objectivity no human could ever match. The James Webb Space Telescope stands as the crowning achievement of this new observational power. Unlike its predecessor, Hubble, which primarily saw invisible and ultraviolet light, Webb is an infrared marvel. This is a critical distinction in the quest for truth. Infrared light has longer wavelengths that can pierce through vast, obscuring clouds of cosmic dust, the very dust that has hidden stellar nurseries and the hearts of distant galaxies from our view. Furthermore, due to the expansion of the universe, the light from the most ancient and distant objects is stretched into the infrared part of the spectrum by the time it reaches us. Webb, therefore, is not just a better telescope, it is a time machine that allows us to see the first glimmers of light after the Big Bang with a clarity we've never possessed. But its raw power is only half the story. The data it sends back is so immense and complex that traditional analysis methods are utterly inadequate. A single deep field image from Webb can contain thousands of faint, distant galaxies, each a potential puzzle. Is that smudge a truly primordial galaxy, or just a clump of nearby dust? Is that strange arc a sign of gravitational lensing, or an artifact of the telescope's own optics? This is where the second pillar of our technological revolution takes over: artificial intelligence. Machine learning algorithms, trained on millions of simulated cosmic images, are now essential partners in this detective work. They can perform tasks that would be impossibly tedious and subjective for a human. For example, in the search for gravitationally lensed galaxies, where a foreground galaxy's gravity bends the light of a more distant one into rings or arcs, an AI can scan thousands of images in minutes, identifying subtle, telltale distortions that even the most trained eye might miss. It does this without getting tired, without having a bad day, and without being influenced by the desire to make a landmark discovery. This reduction of human bias is perhaps the most important contribution of this new technology. These algorithms are also brilliant at separating signal from noise. The cosmos is a noisy place, filled with the static of cosmic rays, the faint glow of zodiacal light, and the instrumental quirks of the telescopes themselves. AI can be taught to recognize and subtract these contaminating signals with incredible precision, cleaning the data to reveal the pristine cosmic message beneath. This allows us to use supernova as more reliable standard candles, to measure the universe's expansion with less uncertainty, and to confirm the existence of exoplanets with far greater confidence, filtering out the red herrings of stellar flares and binary star systems. This powerful synergy between human curiosity and machine intelligence is doing more than just correcting old errors. It is actively opening frontiers we could previously only dream of. By using supercomputers to run incredibly complex simulations of galaxy collisions, dark matter interactions, and stellar evolution, we can create vast libraries of what the universe should look like under different theoretical models. We can then task our AI tools to compare these simulations against the real data collected by our telescopes, not to prove a specific theory, but to see which model most accurately predicts reality. This process of simulation and comparison is a powerful engine of skepticism, constantly testing our most cherished ideas against a cold, digital mirror. The technological evolution in astronomy is a beautiful demonstration of a self-correcting system in action. Each time an illusion fools us, be it the phantom signal of a dark matter experiment or the mistaken alignment of a cosmic string, we are forced to build a better tool, a sharper algorithm, a more rigorous method to ensure it doesn't happen again. This relentless innovation, driven by both our capacity for wonder and our commitment to doubt, ensures that our journey to understand the cosmos is not a straight line to truth. but an ever-tightening spiral, gradually closing in on a reality that is far stranger and more wonderful than any illusion it creates. From the mind-bending gravitational mirages that warp the very fabric of space-time to the phantom radio signals that perfectly mimic alien greetings, these 40 cosmic illusions reveal a universe that is far more cunning and deceptive than we could have ever imagined. They are not simple errors or mistakes in observation. They are the cosmos's most sophisticated magic tricks, performed on a scale so vast they can confound our most advanced technology and our brightest minds. Each one of these deceptions, from the vanishing stars that fake their own deaths to the dark matter signals that evaporate under scrutiny, serves as a powerful lesson in humility. They remind us that no matter how much we learn, the universe will always have another secret, another layer of mystery waiting to reveal itself to those who are both curious enough to look and cautious enough to question what they find. Yet, for every illusion that has tricked us, humanity has demonstrated an incredible capacity for perseverance and ingenuity. The history of astronomy is not a story of getting things wrong, but a story of getting things less wrong over time. Each cosmic deception, once uncovered, has acted as a catalyst for monumental progress. The false promise of antimatter galaxies drove us to build more sensitive gamma-ray telescopes. The phantom planets in our own solar system forced us to develop more rigorous verification methods. The heartbreaking mirage of the BICEP2 signal led to a profound refinement in how we analyze the cosmic microwave background. These illusions are the universe's way of testing our mettle, forcing us to sharpen our tools, refine our theories, and deepen our understanding. They are the difficult puzzles that, once solved, elevate our entire comprehension of reality. This endless dance between deception and discovery is what makes the exploration of space so profoundly thrilling. It is a journey with no final destination, where every answered question simply reveals a dozen new, more fascinating mysteries waiting in the wings. As we stand on the precipice of a new era, with telescopes like James Webb peering back to the dawn of time and AI algorithms sifting through data for clues we might otherwise miss, we must carry forward the twin torches of boundless curiosity and healthy skepticism. Let these 40 illusions inspire you to look up at the night sky with a sense of wonder, but also with a questioning mind. The greatest enigmas are still out there, hiding in the data, waiting for the next sharp-eyed observer to see through the universe's brilliant deceptions and uncover a truth more astonishing than any fiction. We want to hear which of these cosmic tricks surprised you the most. Was it the fact that our solar system might be fundamentally unstable, or that the emptiness of space might be teeming with phantom energy? Let us know your thoughts in the comments below, and if you enjoyed this deep dive into the universe's greatest magic show, be sure to subscribe and hit the bell so you don't miss our next journey to the edge of understanding. If this journey through the universe's greatest magic tricks has left you in awe, do us a huge favor and hit that like button. It truly helps others discover these cosmic conversations. Share this video with a friend who loves a good mystery. After all, the universe's grandest deceptions are even more fun to unravel together. To make sure you never miss out on our next exploration into space's deepest enigmas, tap that subscribe button and ring the bell for notifications. We're always cooking up new content that pushes the boundaries of what we think we know. Now we want to hear from you. Drop us a comment below and tell us which of these 40 illusions blew your mind the most. Was it the way gravity warps light into phantom galaxies, or perhaps the sobering reality that we might be utterly alone in the cosmos despite its vastness? Maybe you've heard of another brilliant deception that fooled astronomers. We're all ears and love learning from this incredible community. Your thoughts and questions are what keep this channel growing, and we read every single one. Never stop gazing at the stars with a sense of wonder, and never, ever stop questioning everything you see. The greatest discoveries always begin with